Good morning, friends. I welcome you to the last, I think it's the last episode of Gravitation. That is solved past paper questions. So I ask you to pull out your document for revision questions so that we wind up with this part of gravitation. Note that using this lesson, it's always better you first pause the video, you try to attempt the question before you reveal the solution as worked out by the teacher. So that will be a better approach to making you understand the concept better. So pull out your document, pull out your master key to A-level physics 9702 revision questions paper 4. And remember, we are on gravitation. We are on gravitation, and we are trying to come out to go through the worked examples and or the solved past paper questions under the unit of gravitation. So pull out your document, and I think we stopped on page 28. Page 28. Yeah, we must have stopped on page 28. If I'm not mistaken, yes. So we had already attempted this particular question. I don't want to go back to it. I just want us to proceed from where we stopped last time. So next, state Newton's law of gravitation. We know that the force between 2-point masses, the force between 2-point masses, the force between 2-point masses The force between 2-point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. That is Newton's law of gravitation. For the number of times we have stated that law, it means by now it should be part of you. You don't even need to revise it to know it. Next, the Earth and the Moon may be considered to be isolated in space, with their masses concentrated at their center. The orbit of the Moon around the Earth is circular, with a radius of 3.84 times 10 power 5 kilometers. The period of the orbit is 27.3 days. Show that the angular speed, that is omega, is 22.66 times 10 power negative 6 radians per second. Of course, by definition, we know that angular velocity, the rate of change of angular displacement, is 2 pi over t. By simple substitution, this will be 2 pi divided by the period. The one mark I think is just for converting the period. 27.3 days times 24 hours times 3,600. I pick my calculator. So by pressing or checking with my calculator, I'm getting 2.66 times 10 power negative 6 radians per second. Okay. The mass of the Earth is 6.0 times 10 power 24. So We want to show that the question is show that the mass of the Earth is 6.0 times 10 power 24. Remember, the gravitational force provides the centripetal force. The gravitational force, since there are only two marks, I'll just say gravitational force Fg provides the centripetal force. So I'm going to equate capital G, capital M for the mass of the Earth, small m for the mass of the Moon, divide by the square of their separation, should be equal to the centripetal force of the Moon. So R squared cancels that, small m was cancelled. So I make capital M the subject. But remember V is omega R, and we have omega above. So capital M is going to be equal to V squared, which is omega R, but this is squared, then times another R, which is here, divided by capital G. So since the radius of orbit was given as 3.84 times 10 power 5 kilometers, I will simply substitute. So I'm substituting omega. Note that this will be omega squared. So this is 2.66 times 10 power, omega is negative 6, but this is squared. This is r squared times r, which is r cubed. So this will be times 3.84. It was given in kilometers, so I have to multiply by 10 power 3. So it becomes 10 power 8 divided by 6.67 times 10 power negative 11. I have to press my calculator. So when I press my calculator, I'm just verifying that is to two significant figures, 6.0 times 10 power 24. Now I want you to note that whenever a question tells you to show something, don't think that just arriving at this value is what gives you the 2 marks. In fact, writing this value here carries no mark. It's correct working and correct substitution. The examiner will check if your substitution arrives at the value given or the value required. Part C, the mass of the Moon is 7.4 times 10 power 22 kilograms. Using data from B, determine the gravitational force between the Earth and the Moon. So just one force, that is Newton's law of gravitation. The force between the 2 point masses will be capital G, capital M, small m over r squared. When we substitute, G is 6.67 times 10 power negative 11. Capital M is 6.0 times 10 power 24. Small m is 7.4 times 10 power 22. Divide by r squared. R is 3.84 times 10 power 8, but this is squared. So we press our calculator. So by pressing my calculator, I'm arriving at 2.0 times 10 power 20 newtons to two significant figures. Okay, part 2. Tidal action on the Earth's surface causes the radius of the orbit of the Moon to increase by 4 centimeters. To increase by 4 centimeters each year. Use your answer in Roman 1 to determine the change in 1 year of the gravitational potential energy of the Moon. How does the gravitational potential energy change? If the change in radius, or the radius increases by 4 centimeters each year, How does, or use your answer in Roman 1 to determine the change in 1 year of the gravitational potential energy of the moon. Okay. Okay, so since we are going to use the answer above, so the change in gravitational potential energy, delta P, I want to write this as a subscript so that people don't misinterpret it. So the change in gravitational potential energy is going to be, of course, this is work done, which is going to be force times the distance x. And because this change here is very small compared to the radius of orbit, then it means the force is approximately constant. So we are saying the force F is, we are going to use work done as force times distance because F is approximately constant since the change in the radius of orbit is very, very small and therefore approximately the same as the radius of the orbit that we had before. So F, we shall use F times X. I'm saying because they said explain your working. So this is because F is approximately constant. The force F will be considered to be constant since X will be approximately the same as the radius of orbit. Since the force is constant, since the distance, the new distance from the center will be approximately equal to the radius of the orbit. So the force F will be approximately constant. Or I can say since R, let me use R because I've used X here, so let me use R. Since R is approximately equal to the radius of orbit. So note that initially if the radius of orbit is equal to R, then when there is a change of 4 centimeters, the new radius of orbit is going to be R plus 0. R plus 4 centimeters or 0.04 centimeters, which is approximately the same as R. This means G is approximately constant and therefore F is approximately constant. So it means the change in potential energy, delta P, is going to be equal to the force that we have obtained above, 2.0 times 10 power 20. Then we multiply this by the change in height, which is 4.0 times 10 power negative 2. So that will be the work done. This is change in distance, x is the change in distance or the change in the radius of orbit. When I press my calculator, so this is directly 8.0 times 10 power 18. 8.0 times 10 power 18. Alternatively, you could go direct. You could go back to the same expression above. And although they say to use this answer, of course, somewhere, somehow, you'll have the force to be still this, and then you multiply by the change in height. Let's try that and see. So I am going to rub off what I've already just done here so that I use the same space. Okay, so let's see. At the first height where the radius is r, I will call it r1. At a new height, the radius will be r2. where R2 is R1 plus 4 centimeters. So the change in gravitational potential energy, remember, is equal to capital G M over, this will be R1. Note that is going to be negative. Let's say, of course, it is high at a higher level, so this is negative R2 minus negative G capital M small m over R1. I wanted to just show you that this becomes, there's a common factor of capital G capital M small m into, this becomes positive. So it is 1 over R1 minus 1 over R2. So when I continue this further, you cross multiply here, so this becomes capital G capital M small m into, so this is going to be R2 minus R1, which is over R1 times R2. Okay, so this is going to be capital G capital M over, note that R1 times R2, R1 times R2 is approximately the same as R squared. We can check, but anyway, you can verify. Because this is 4 centimeters, so the product here is going to be R2 minus R1 is 4 centimeters, so this is going to be 4 times 10 power negative 2 squared. But we are saying R1 times R1 R2 is the same as R1 R2 squared, I mean R1 squared or R2 squared or R squared. So this is R squared. In other words, let me put this in brackets. I'm saying R1 times R2 is approximately the same as R squared. You can put that in the calculator. Remember, R2, you add 4 centimeters. Then R1 was 3.84 times 10 power 8. So add 4 centimeters to 3.84 times 10 power 8. And when you multiply the two, you get approximately R squared. But note that we have obtained this here. We have obtained this quantity here from the previous part, which is approximately that. So it is the same as just saying 2.0 times 10 power 20, then times 4 times 10 power negative 2. As simple as that. This takes you to 8.0 times 10 power what? Power 18, as we obtained earlier on. So here I don't need even to explain that F is constant, since R, the radius, the distance to a height of to the point where the increase is 4 centimeters is approximately the same as the radius of orbit initially. Here everything is self-explanatory, just substitute. Okay, so energy change is that. State Newton's law of gravitation, the force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. Okay, so such questions are a repeat. That was intentional, but maybe in another volume which your siblings will use, I will make sure that questions are not repeated. But this repeat is also good for people to get comfortable and confident with the concepts. Okay, a star and a planet are isolated in space. The planet orbits the star in a circular orbit of radius r, as illustrated. Okay, the angular velocity is clockwise. The angular speed of the planet about the star is omega. By considering the circular motion of the planet about the star of mass m, show that omega and r are related by that expression where g is the gravitational constant. Okay, so all we know is that the gravitational force provides the centripetal force. The gravitational force provides the centripetal force. The gravitational force provides the centripetal force, and if this is true, then capital G, capital M, small m over r squared. Now we shall use capital R for the radius of orbit is equal to small m's v squared over capital R. That is centripetal force. And of course, we know that speed v is equal to omega times r, and it is squared. So this has cancelled with that. This has cancelled with that. So we now have that capital G, capital M over R is equal to, this is omega squared, or omega times R, but this is squared. When you open the brackets, you have that G capital M is equal to omega squared R squared times R, which becomes omega squared times R cubed as required. The Earth orbits the Sun in a circular orbit of this radius here. The mass of the Sun is 2.0 times 10 power 30. A distant star is found to have a planet that has a circular orbit about the star. The radius of the orbit is 6.0 times 10 power 8 kilometers, and the period of the orbit is 2 years. Use the expression in B to calculate the mass of the star. So the Earth is orbiting the Sun. A distant star is found to have a planet that has a circular orbit about the star. The radius of the orbit is given as that, and its period is that. So we want to use the expression in B to find the mass of the star. Okay, so using this expression here, using that expression there, we can compare the two equations. Since we have the mass of the Sun and the radius of orbit of the Earth, and we have the radius of orbit of a star around a planet, then we can use the same ideas to be able to find the mass of the star. How? If I consider the star first, then I will say the mass of the star times the gravitational constant, capital G, I'm using this expression here, will be equal to the radius of that star, which I will call r cubed, times its angular velocity. So this is r for the star times the angular velocity, which we are saying it is omega squared. And this is for the star. Because the Earth, a distant star is found to have a planet that has a circular orbit about the star. The radius of the orbit is this, and the period of the orbit is 2.0 years. Use the expression in B to calculate the mass of the star. We know that the period of the Earth around the Sun is 1 year. Period of the Earth is 1 year. That one is known by everyone. So if I consider, remember omega is 2 pi over t, and we want period. If I consider the Earth or the mass of the sun, I will say the mass of the sun, because the earth is orbiting the sun, the mass of the sun times capital G is going to be equal to the radius cubed of the sun times the angular speed of the earth around the sun. This is radius of orbit of the earth around the sun times the angular speed of the earth around the sun. Remember, omega is 2 pi over t since we want period. Now I'm going to substitute. I'm going to divide these two equations as I substitute 2 pi over t. So mass of the star divided by mass of the sun, G has cancelled, is equal to the radius cubed, radius of orbit of the star or around the star over the radius of orbit around the sun by the earth times, where there is omega of the star, we'll put there 2 pi over the period of the star, divide by, where there is omega squared of the sun, I will say period around, 2 pi divided by the period around the sun. Note that this is squared and this is squared. So when I simplify this, I will simplify by direct substitution. So radius around the star is 6. I will not change because they are both in kilometers. So I will simply say 6.0 times 10 power 8. This one is 1.5 times 10 power 8. That is radius around the star is this, radius around the sun is that. Then times, you notice that when I divide this by this, 2 pi cancels and the period of the sun goes up, whereas period of the star remains down. So this becomes period of the sun divided by period of the star. But note that this is squared. By the way, this was cubed. Okay. When I try to simplify this, this is 6.0 divided by 1.5. I think that is 4. I guess 6.0. 6 divided by 1.5. I think that is 4. So I have 4 cubed times period of the sun is 1 year, period around the sun is 1 year, period around the star is 2 years. So this is 1 over 2 raised to power 2. So I'm trying to find the mass of the star. So I will multiply this by the mass of the sun. So the mass of the star is going to be 16. This one by power half over 4 times the mass of the sun. We are cross multiplying, of course. So this will be times 2.0 times 10 power 30. Let me press my calculator. 16. By the 4 cubed can't be 16. This is 64, not 16. 64 by 4 times 2. So I am getting 3.2 times 10 power 30. No, not 30, 31. So it's dangerous to follow this video as you just write in your documents. Better if you try out using a pencil, and if you notice that you can't arrive, or you try to mark yourself by watching how the question was solved, and before you write you have to watch how the solution moves up to the end, so that you don't keep crossing or rubbing your work, making the book to look untidy. Okay. So the mass is that. So I just use simple algebra and I arrived at that. Define gravitational potential. This is the work done in moving a unit. This is the work done in moving a unit mass. From infinity a unit mass or a unit test mass from infinity to the point we are talking about. This will be automatically in the gravitational field. Okay, number next. The moon may be considered to be an isolated sphere of radius 1.74 times 10 power 3 kilometers with its mass 7.35 times 10 power 22 kilograms concentrated at its center. A rock of mass 4.5 kilograms is situated on the surface of the moon. Show that the change in gravitational potential energy of the rock in moving it from the moon's surface to infinity. Note that infinity potential is zero, so we shall simply say change in potential energy is equal to at infinity to be zero minus, elsewhere it is negative, capital G, capital M, small m over r. That is the gravitational potential at a point. So this becomes positive, so this will give us 6.67 times 10 power negative 11 multiplied by capital M 7.53, sorry, 35, 7.35 times 10 power 22 divided by the orbit, radius of orbit is going to be 1.74 times 10 power 3, then times 10 power another 3 to change it to meters. And when I press my calculator, so that is 10 power 6, press the calculator, so from pressing the calculator I get 1.27 times 10 power 7 joules. You can verify. Oh, by the way, this is times. I had multiplied this in the calculator and forgot to write it here. So times 4.50 because it is capital M times small m. Okay, the escape speed of the rock is the minimum speed that the rock must be given when it is on the moon's surface so that it can escape to infinity. Use the answer in Roman 1 to determine escape speed. So if this is the minimum energy required for it to leave the surface of the moon, so then it will be the minimum speed if when exceeded if as soon as it is exceeded, then the rock escapes to infinity. So it means a half mv squared should be equal to the change in potential energy. That is 1.27 times 10 power 7. So that means V is going to be 2 times 1.27 times 10 power 7 divided by M. M was given as 4.5, the mass of the rock, under the square root. Calculator. This is 2.4 times 10 power 3 meters per second. 2.4 times 10 power 3 meters per second. The moon in B is assumed to be isolated in space. The moon does, in fact, orbit the Earth. State and explain whether the minimum speed for the rock to reach the Earth from the surface of the moon is different from the escape speed calculated in B. Of course, obviously, it must be different. Reason? Before even the rock left the moon, it was already experiencing a force of attraction by the Earth. That means the actual speed should be less than that because it was already being attracted. That means it would require a less speed than that. So we are saying the Earth would attract the rock. So the speed is going to be low. In other words, before the rock left the moon's surface, it already had a force of attraction by the Earth. So the Earth would attract because the Earth's gravitational field extends up to the moon. So the Earth would attract the rock. So the escape speed is going to be lower. The escape speed would be lower. So it needs a smaller speed to launch you from a certain point above the Earth's surface to the Earth because already the Earth is exerting a force on you. So you would require little speed to leave the surface of that point or to leave another planet if you are moving towards another where there is a gravitational force or attraction between the two. Alternatively, the potential, of course, at the surface of the moon, the potential is not zero. Yet when we are calculating this, we equated kinetic energy to the change in potential from considering the center, but at the surface, the potential is not zero. Potential due to the moon is not zero. Even at the Earth's surface, potential due to the moon is not zero. Therefore, if the potential due to the moon is not zero, that means there is already potential energy at the Earth's surface due to the moon, and this would make the speed to be actually lower. So another password, by the way, this also implies the first one. So I would simply say alternatively, at the Earth, at the Earth's surface, potential due to the moon is not zero. Potential due to the moon is not zero. So the escape speed would be lower. The escape speed would be lower or would be smaller because already potential due to the moon, potential at the Earth's surface due to the moon is already not zero. So it means the escape speed would be lower than what we have just obtained. However, if it was to be zero, maybe it would be exactly what we have obtained. But since the potential at the Earth's surface due to the moon is not zero, then it means the escape speed will be lower than what we have calculated. Next, gravitational field. What is meant by gravitational field? This is a region of space. Region of space. Region of space where a mass experiences a force. Region of space where a mass experiences a force, maybe due to another mass. Region of space where a force is experienced due to a mass. That is what we call a gravitational field. In the solar system, the planets may be assumed to be in circular orbits about the Sun. Data for the radii of the orbits of the Earth and Jupiter about the Sun are given in the figure. State Newton's law of gravitation. You will get tired of stating this, but the more you state it, the more confident you become about it. So the force between 2 point masses is directly proportional. Is directly proportional to the product of the masses and inversely proportional to the square of their separation. Use Newton's law to determine the ratio gravitational field strength due to the Sun at orbit of the Earth, gravitational field strength due to the Sun at the orbit of Jupiter. So just look at the radii of orbit due to the Sun at the orbit of the Earth, due to the Sun at the orbit of Jupiter. Note that the Earth and Jupiter orbit the same Sun, therefore the constant of proportionality is going to be the same. So gravitational field strength is equal to capital Gm over r squared. Now this will be the same because it is not depending on, because we are finding due to the Sun at the orbit of the Earth and due to the Sun at the orbit of Jupiter. So G times m is going to be a constant. So if I consider the Earth, G due to the Sun on the Earth is going to be capital G m over radius of orbit of the Earth squared, and the G due to Jupiter is going to be capital G m over radius of orbit of Jupiter around the Sun squared. So when we divide the two, G due to the Sun at the Earth over G due to the Sun at Jupiter. We are dividing these two equations. The constant Gm cancels, so G Jupiter goes up. So it is r G Jupiter squared over r radius of orbit of the Earth squared. We simply substitute from the table above. Jupiter is 7.78 times 10 power 8. The Earth is 1.50 times 10 power 8, and this is squared. So you just press the calculator here. So this is giving me 27. So I'll just write here 27 as the ratio. Next, the orbital period of the Earth about the Sun is T. The orbital period of the Earth about the Sun is T, capital T. Use ideas about circular motion, that is centripetal force or centripetal acceleration, to show that the mass, capital M of the Sun, is given by that expression. Explain your workings, so you just say gravitational force. Gravitational force provides centripetal force. Gravitational force provides centripetal force, so capital G, capital M, small m, over, they use the capital R, so shall we say capital R squared is equal to, for the Earth, this would be small m v squared over capital R squared. Remember, v is equal to omega times r, so I now substitute, and omega is 2 pi over t, then this is times r. So small m was already cancelled, so capital G, capital M over this one, by the way, this is not squared. This one reduces that, so this remains with r equals to, where there is v squared, I'll put there 2 pi over t times r, and this is squared. We simply open up and do the algebra. So opening up or cross multiplying, you have that capital GM is equal to 4 pi squared r squared over t squared. This is over r. Cross multiplying, m is going to be 4 pi squared r cubed. Divide by t squared and divide both sides by g as required. The orbital period t of the Earth about the Sun is given by that in seconds. The radius of the Earth's orbit is given in the figure 1.1, which is the table here. Okay. Use the expression in Roman 1 to determine the mass of the Sun. So we're just substituting to determine the mass of the Sun. So the mass of the Sun will simply be equal to 4 pi squared times the radius of orbit, 1.5 times 10 power. It was given in kilometers, so I multiply by 10 power 3. It becomes 10 power 11 in meters. Divide by g, 6.67 times 10 power negative 11. Multiply by t squared. They say the period is that, so, and it's already in seconds, so I'll just say 3.16 times 10 power 7, and this should be squared. Of course, we have an idea about the theoretical mass of the Sun, so we are just verifying. So my calculation is giving me 2.0 times 10 power 30 kilograms, two significant figures. What is meant by a geostationary orbit? Geo referring to the Earth. So this is an orbit which is above the equator. So orbit above the equator, or it's in equatorial orbit. Equatorial orbit, that is above the equator. Number 2, it moves, if it is a satellite, it moves west to east. So say I would just use satellite moves west to east for the object. Satellite moves west to east, or satellite moves in the same direction as the rotation of the Earth, or as the spinning of the Earth about its axis. Number 3, we know that the period is 24 hours. In other words, it takes the same time as the period of spinning of the Earth. So those are the 3 important features of a geostationary orbit: west to east, above the equator, period of 24 hours. Next, a satellite of mass m is in circular orbit about the planet. The mass m of the planet may be considered to be concentrated at its center. Show that the radius r of orbit of the satellite is given by that expression. So this is very easy, but the space is not favoring me anyway. The gravitational force provides the centripetal force. The gravitational force, I'll just write Fg, provides the centripetal force Fc. So I'll simply equate the two, capital G, capital M, small m, over r squared is equal to small m v squared over r. So small m has cancelled, this one has also cancelled. We know that v is equal to omega times r, which is equal to 2 pi r over t. So we substitute, so capital G, capital M over r is equal to 4 pi squared r squared over t squared. And we cross multiply, making r cubed the subject. So G m t squared is equal to 4 pi squared r cubed. So r will be equal to G m t squared divided by 4 pi squared. So you see it is almost the same question every time. Almost the same question every time, the same question every time. The Earth has mass of 6.0 times 10 power 24. Use the expression given in B to determine the radius of the geostationary orbit. Okay, so that is also very easy. By that, this is r cubed. So r cubed is going to be equal to, I'm just substituting, G is 6.67 times 10 power negative 11. M is 6.0 times 10 power 24. Then T is period of gestation is 24 hours. So it is 24 times 3600. And this is squared. Divide by 4 pi squared. So this is giving me so r cubed is 7.57 times 10 power 22. So this will be meters cubed. But we want radius, so we get the cube root. So r will be the cube root of 7.57 times 10 power 22. And this gives us 4.2 times 10 power 7. Of course, that value is now common to us, so we can always have a theoretical idea that a geostationary orbit is at a distance of approximately 4.23 times 10 power 7 meters from the center of the Earth. Next, on the axis of the figure 2.1, sketch the variation with the distance from a point mass. For a point mass, G varies inversely proportional to the square from the surface. They want sketch the variation with the distance from a point mass of the gravitational field strength due to the mass. So we want variation with distance from a point mass. So this is obviously, of course, since we can't go deep into the center of the point mass, so I'll have a boundary somewhere here to use as my reference point. Or in other words, my value of G will not start from the origin. So G varies as inversely proportional to the square of the distance. So it starts from a certain value. So I have to draw a smooth curve, not going to 0, of course, on the y-axis, because that will not be to be something like this. Starting with a certain value on the surface. Of course, we know what happens inside the surface. Inside it is a different case, but outside G varies as the inverse square. because as the distance changes, G also decreases. As simple as that. So it is supposed to be a smooth curve with a decreasing gradient. It should not be touching x equals to 0. It cannot touch x equals to 0. Not touching x equals to 0. If it touches x equals to 0, it means something different. It means something different. And the line does also not touch g equals to 0. You cannot make it to touch the x-axis. It means you are sure of a distance where g becomes 0. Yet g becomes 0 at infinity. So if it touches the x-axis, does it mean you have already reached infinity? So it doesn't touch both axes. Then next, on the axis, sketch the variation with the speed of the magnitude of the force on a charged particle moving at right angles to a uniform magnetic field. We shall see this in magnetism, but just for completeness, force is equal to BQV, where B is the magnetic flux density perpendicular to the surface, that is, B is normal, or the component of the magnetic field perpendicular to the what? To the surface, or perpendicular to the area. And you will notice that F is just directly proportional to V. That means it is a straight line through the origin. So F varies from 0 to a certain value or to maximum as V increases. So that is a straight line from the origin. Can't I borrow a straight line from the tools? But I can draw it, no problem. It's only that I don't have a ruler, but I'll try. So you can draw a straight line from the origin, wherever you want. You can make it go up to where you want. So that is a straight line from the origin because the force, the magnetic force, is directly proportional to the speed. The faster a particle moves, the greater the force it experiences in a uniform magnetic field. We shall see this in magnetism. Then next, so it should be a straight line. Let me write it here, straight. It should be a straight line. Of course, it has a positive gradient. And starts from the origin. Starts from the origin. Okay, next. Next is on the axis, sketch the variation with the time t of the power dissipated in a resistor by a sinusoidal alternating current. Of course, we shall see this in alternating current, but maximum power P naught is equal to I naught times V naught, where I naught and V naught are peak values, and power dissipated is always going to be actually a constant value, because when you look at I naught and V naught, these are values, these are peak values, and the peak value is the value which has the same effect as direct current. I mean, as is the value of the alternating current which has the same heating effect as the direct current. We shall see that in alternating current. And the power will always be positive. From alternating current, we shall see that I is equal to I naught sine omega t, that is sinusoidal current. And we shall also see that V is equal to V naught sine omega t. So remember, power is equal to I times V. These two always change sign. And when I is negative, V is negative, the power is positive. When I is positive, V is positive, the power is positive. What does that mean? The power is always a positive value. And of course, if I get I times V to be, this will be equal to I naught times V naught sine squared omega t. And of course, this is a sine, the square of the sine curve. So it is going to be a sinusoidal graph. It is going to be a sinusoidal graph, but has a maximum value at I naught times V naught, which is the peak value of power. Then it varies with the square. So that means I have, they said for two cycles. So I'm going to draw, I think every cycle, because if this is the current, I'll just draw this as the current. That is one cycle. That is another cycle. If this is current or V, because they are always directly proportional. Then for power, for the first half cycle, the power is positive. For the second half cycle, where current becomes negative, still the power remains positive. So for the half cycle, power is positive. For the second half cycle, power is still positive. For the next half cycle, power is still positive. For the next half cycle, power is still positive. So those are two complete cycles of current. So I'm going to just divide this into 1, 2, 3, 4. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 2, 4, 5. 2, 4, 5. 2, 4, 5. 1, 2, 3, 4, 5. Okay, so I can say each cycle takes 10 small squares. I mean, each half cycle, I don't know whether they will reach for 10, 20, 30, 40. 10, 20, 30, 40. I think that is enough. That will be enough. But then they have the same peak, the same maximum. So they should not go beyond a certain point. So I can draw a reference point here along with this. My graph should not go beyond this point here. Okay, so now I can start sketching. Okay, so that is, I think it's a fair sketch. You can sketch one which is better. So this is half a cycle, half a cycle. No, this is not true. This is going to be not true if I make this very big. Okay, so that is the graph for power against time. We shall see that in a unit called alternating current. The power will always be positive. So I've done this just for completeness, just for our document to be completed, but we shall see this under alternating current. Okay, next. An isolated sphere, an isolated spherical planet has a diameter of 6.8 times 10 power 6 meters. Its mass of 6.4 times 10 power 3 kilograms may be assumed to be a point mass at the center of the planet. Show that the gravitational field strength at the surface of the planet is 3.7. So gravitational field strength, that is small g, is equal to capital G, capital M over r squared. We substitute 6.67 times 10 power negative 11 times 6.4 times 10 power 23 divide by the square of the separation. They gave us the diameter, but we are finding at the surface, so we divide this by 2. So it becomes 3.4 times 10 power 6, and this is squared. Pick our calculator. So this is giving me 3.7 newtons per kilogram. You can verify. A stone of mass 2.4 kilograms is raised from the surface of the planet through a vertical height of 100 meters. Remember, the radius is 3.4 times 10 power 6. The height of 100 meters is very, very small. That means G can be considered to be constant. Use the value of field strength G given in A to determine the change in gravitational potential energy. Explain your answer. This is one full mark. So it means since the change in height is far, far smaller, the change in h is far, far smaller than the radius. Change in height is far, far smaller than the radius, then g is approximately constant. G is approximately constant, equal to a constant. And if G is approximately equal to a constant, then it means I can now use the other expression that we saw in AS. The change in gravitational potential energy can now be equal to mg times change in height. When the change in height is far, far smaller than the radius, then G is almost the same. And if this is true, I just substitute. So the mass is 2.4 times G is 3.7 times change in height is 1800. So this is giving me a 1.6 times 10 power 4. You can verify. Next, a rock initially at rest at infinity. A rock is initially at rest at infinity. That means it has potential energy 0. Now moves towards the planet at point P. Its height above the surface of the planet is 3D. So its height above the surface of the planet is 3D, where it is the diameter of the planet. Okay, as shown in the figure. Calculate the speed of the rocket at point P. Calculate the speed of the rocket at point P. So we can say that the loss in gravitational potential energy is equal to the gain in kinetic energy. So the loss in gravitational potential energy at infinity is 0 minus negative. Elsewhere it will be G, capital M, small m over R. We have already seen that. Elsewhere potential energy is potential times the small mass. This should be equal to a half m v squared. So small m has cancelled. We don't need it. This becomes positive. So it means the speed v squared is going to be equal to capital G, or twice capital G, capital M over R. Then we find the square root. So v is going to be the square root of 2 times 6.67 times 10 power negative 11 times capital M. The mass was given in the previous part as 6 point, what was the mass? The mass is given as 6.4 times 10 power 23 kilograms. 6.4 times 10 power 23 kilograms. This is divided by r, radius of orbit. So they said this is the diameter of the planet. The radius, or the distance from this point here to that point there, is equal to 3.5 d plus a half of the diameter, 0.5 d, which is equal to 4.0 d. So the radius of the distance from P to the center, which is R, is actually, by the R is not meaning radius here. It is distance from the center to the point where we have moved our mass to. So this is going to be 4d, which is 4.0 times d was diameter, 6.8 times 10 power 6. Press the calculator. So pressing the calculator is giving me V as 1.8 times 10 power 3. So speed is 1.8 times 10 power 3 meters per second. Define gravitational potential, the work done in moving a unit test mass from infinity to the point. The work done in moving, or to move, a unit test mass from infinity to the point. A stone of mass m has gravitational potential energy EP at a point x, the gravitational field. The magnitude of the gravitational potential at x is phi. State the relation between m, EP, and phi. We know that potential energy is potential times the test mass. So EP is going to be equal to the mass times the phi. But note that the potential is always negative, so this will be minus. So the potential energy is going to be minus, because potential is always negative. So let me even correct this. If you forget the minus, you don't get that 1 mark. So EP is equal to negative mass times phi. The negative there is very important. An isolated spherical planet of radius r may be assumed to have all its mass concentrated at the center. The gravitational potential at the surface of the planet is given by this. A stone of mass 1.3 kilograms is traveling towards the planet, such that its distance from the center of the planet changes from 6r to 5r. Calculate the change in gravitational potential energy of the stone, 4 marks. The change in gravitational potential energy of the planet. So we know that potential is given by negative capital Gm. I will use x for distance from the center to the point. And this has been given as negative 6.30 times 10 power 7. That is the potential on the surface. That is potential on the surface where the distance is r from the center. And potential at a distance 6r is traveling towards the plan so that its distance from the center. So 6r, this means, oh, by the way, this will be now r. So 6r will be negative g. I will make this one r, negative gm over 6r, which becomes negative of gm over, so this is 1 over 6 r. I can leave the negative inside so that people can see it correctly. So this is 1 over 6 into negative that, and this is going to be 1 over 6 times 6, or negative 6.30 times 10 power 7. That means also potential at 5r is simply going to be 1 over 5 times negative 6.30 times 10 power 7. So we want the change. We can find the change in potential and then find potential energy. Remember, potential energy is mass times change in potential. So the change in potential is going to be, what is this value here? So this is 1.05 times 10 power 7. Potential is joules per kilogram. And this one is 1.26 times 10 power 7 joules per kilogram. The change in potential will simply be 1.26 minus 1.05 times 10 power 7. That is the change in potential. Then the change in gravitational potential energy will be equal to the mass times the change in potential. Now this one will be positive. So this will be 1.3 times, what is that difference? 1.26 minus 1.05. So times 0.21 times 10 power 7. Answer. So this is giving me 2.7 times 10 power 6 joules. 2.7 times 10 power 7, no, power 6. Alternatively, somebody would get this directly from change in potential energy is equal to mass times change in potential, which is going to be equal to mass, times change in potential, which will be capital G, capital M over R. This will be at a certain height minus the one at another height. But notice that, so this will be R into 1 over 5 minus 1 over 6. And this one here is 6.30 times 10 power 7. So you get 1.3 times 6.3 times 10 power 7. Then you simplify this. You'll get the same answer down there. Here I've just used mathematics, factorizing. Note that this is 5r, the other one is 6r. When I pull r out, I get gm over r, which is the same as this, potential at the surface. Okay, the mass m of a spherical planet may be assumed to be a point mass. at its center, at the center of the planet. A stone traveling at a speed v is in a circular orbit of radius r about the planet as illustrated in the figure below. Okay, this is the illustration. Show that V is equal to that. I think that is very easy. Explain your working. When I see that, I know that the gravitational force provides the centripetal force. And if that is true, capital G, capital M, small m over r squared is equal to small m V squared over r. So m has cancelled, r has cancelled, making V the subject. V is equal to, or V squared is equal to capital G, capital M over r, which implies that V is the square root of capital G, capital M over small r. The second stone, initially at rest, at infinity, travels towards the planet as illustrated. So here we had a planet here and the stone was moving around. Another one is now coming from infinity and is traveling towards the planet as shown. The stone does not hit the surface of the planet. Determine in terms of the gravitational constant g and the mass capital M of the planet the speed v naught of the stone at a distance x from the center of the planet. Explain your working. Determine in terms of gravitational constant g and the mass m of the planet the speed v naught of the stone at a distance x from the center of the planet. So if it comes from infinity, there is loss in gravitational potential energy. When it loses gravitational potential energy, it gains kinetic energy. So we shall say the change in gravitational potential energy must be equal to the change in the kinetic energy. Or a loss in gravitational potential energy, this change is actually a loss. And this change will be actually an increase. Because when it is coming from infinity, it is losing its potential energy, since potential energy is maximum at infinity. And as it comes in the direction of the field, it means it gains kinetic energy because it is being accelerated in the direction of the field. It's like when a stone is falling to the Earth's surface, kinetic energy increases as the potential energy decreases according to you. So it means I will simply say, starting from this side, I will simply say that a half m v half m, let me call it v naught squared, is going to be equal to, of course, at this point here, at x has speed v naught, so half m v naught squared is the kinetic energy at that point, is equal to the change in gravitational potential energy, which now becomes g m over x. Small m has cancelled. So it means we have that v naught squared is equal to twice gm over x. So v naught is the square root of twice gm over x. So they wanted it in terms of gm, v naught, and x. So we have obtained that. Use your answer in Roman 1 and the expression in A. The expression in A, which is this, to explain whether this stone could enter a circular orbit about the planet. Now, v naught, the distance from the center is x. For v, the distance was equal to the radius of orbit, which is r. The radius of orbit v, the radius of orbit is r. Determine in terms of the gravitational constant g and the mass m of a planet, the speed v0 of the stone at a distance x from the center of the planet. Explain your working. You may assume that gravitational attraction on the stone is due only to the planet. So they are saying using your answer in Roman 1, which was v is equal to the square root. In Roman 1, we have that v is equal to the square root of g m over r. And we are seeing in Roman 2, v0 is equal to the square root of twice gm over x. To explain whether this stone could enter a circular orbit about the planet. So when you look at these two expressions, this one and this one here, you will notice that g naught is always going to be greater than g because of this factor 2 here. G is always going to be greater than v naught is always going to be greater than v because of this factor here. So if x is equal to r, v naught will always be greater than v. So if that is true, it means the stone could not enter into the orbit. The stone could only enter the orbit if v is equal to v naught. So we are saying that v naught is always greater or is greater than v for x equals to r. V naught is greater than v for x equals to r. So what does that mean? So the stone could not enter into orbit. It could only enter if v naught is equal to v for x equals to r. But since for x equals to r, we notice that because of this factor 2, v naught is always greater than v. So the stone could not enter into orbit. The Earth may be considered to be a uniform sphere of radius 6,380 kilometers, with its mass 5.98 times 10 power 24 kilograms concentrated at its center. So they have showed us this diagram. They have showed us the equator. A mass of 1 kilogram on the equator rotates about the axis of the Earth with a period of 8.6 times 10 times 10 power 4 seconds. Calculate to 3 significant figures the gravitational force Fg. So gravitational force is given by Newton's law of gravitation. So this is capital G, capital M, small m over r squared. So this would be 6.67 times 10 power negative 11 times the large mass is 5.98 times 10 power 24. The small mass is 1.0 kilograms. The square of the separation, they gave us 636,380 times 10 power 3 because it was in kilometers and this is squared. The radius is 6,380 kilometers. I'm pressing the calculator. So pressing the calculator, V is 9.80 to 3 significant figures, newtons. The centripetal force, Fc, on the 1.0 kilogram. Centripetal force Fc. So centripetal force is given by mv squared over r. But remember, V is omega r. So this is m omega times r squared over r, which is Remember, this is going to be m omega squared times r. One r cancels with that. But also remember, omega is 2 pi over t. Omega is 2 pi over t, since they have given us period but not omega. So this is going to be equal to m into 2 pi over t, which is squared times r. So it is m times 4 pi squared over t squared times r. Now I'm substituting. The centripetal force is going to be m. M is 1.00 kilograms times 4 pi squared times the radius of orbit, which is 6380, times 10 power 3 to change it to meters, divide by the square of the period, that is 8.64 times, 62, 8.62 times 10 power 4, and this is squared. So when I press my calculator, so this is giving me 0.0339. Remember, they said to 3 significant figures. Then the difference in magnitude of the forces, difference. So this is going to be centripetal force Fg minus, a force due to gravity minus centripetal force, which is, I'm subtracting. So this was 9.80 minus 0.0339. So this is giving 9.77 newtons. By reference to your answer in A, suggest with a reason a value for the acceleration of free fall. We all know that acceleration of free fall or acceleration due to gravity is the force acting per unit mass. It is actually the resultant force acting on the body per unit mass, which we have already obtained. So the answer for the acceleration is going to be 9.77 meters per second squared, because note that we have found the resultant force on 1 kilogram. So it is force per kilogram. So this is because acceleration is the resultant force per unit mass. Resultant force per unit. Resultant force per unit mass. Okay. State Newton's law of gravitation. The force between 2 point masses is directly proportional. The force between 2 point masses is directly proportional to the product of the masses and inversely proportional to their separation. So that is Newton's law of gravitation. These questions are the same. But because I'm determined to finish this document, I will not skip any. So the gravitational force, some of the planets in the solar system have several moons or satellites that have circular orbits about the planet. The planet and each of its moons may be considered to be point masses. Show that the radius x of a moon's orbit is related to the period t of the orbit by the expression that. So the radius of orbit is x. So this time we shall not use r. Explain your working. That is one mark. So gravitational force. The gravitational force provides. So gravitational force provides centripetal force. The gravitational force provides centripetal force. So capital G, capital M, small m, divided by, now this will be x squared, will be equal to mv squared over x. Remember, v is going to be equal to omega times x, because now the radius of orbit is x, and omega is 2 pi over t. So this is 2 pi over t times x. So we now substitute, this m has cancelled, this square has cancelled. So we have gm over x is equal to 2 pi x over t, and this is squared. So when I try to simplify this, or just cross multiply, I have that g times m is equal to, squaring this, get 4 pi x squared over t squared. This is over x. So when you simplify, make gm the subject, it's notice that gm is going to be equal to 4 pi squared, by the way, this is squared, pi squared times x cubed over t squared as required. Okay. The planet Neptune has 8 moons, each in a circular orbit of radius x and period t. The variation of t with the t squared of x cubed for some of the planets, some of the moons, is shown in the figure. So it means I have to first of all condense this. Okay, I don't know whether it is visible. I know some of you watch these on phones, which is quite unfair. But that is being, I know some of the parents are very mean with the money. And if you're there thinking that the Cambridge curriculum is the same as the national curriculum, I feel sorry for you. It's completely not. Passing here is very hard. You must be hardworking and ready to invest some money into Cambridge. You can't tell me you can't afford to get a simple computer to view the lessons from. Not at all. So I've tried to minimize this so for you can try to maximize to get to see full screen on your computer. Use the figure and expression in B to determine the mass of Neptune. We want to determine the mass of Neptune. First of all, the expression we have obtained is that capital G, capital M is equal to 4 pi squared x cubed over t squared. That is the expression we have obtained. Then the graph we have is t making x cubed the subject, x cubed is equal to gm times t squared over 4 pi squared. You see that we have on the y-axis, we are comparing with y is equal to mx plus c. So here we have no intercept because it is x cubed against t squared. So we have no intercept, so we don't have this part c. So you realize from here that the gradient is going to be equal to, m is the gradient, is g capital M over 4 pi squared. So you can simply say that the gradient is equal to capital G capital M over 4 pi squared. So that is the gradient. And this is going to be equal to, I'm substituting. Since the line is straightly coming here, it is also straightly coming here. And I think this is 4.5 and this is 1.3. So the gradient is going to be 4.5 minus 1.3. That is on the y-axis. By the way, this will be times 10 power 14. That is in kilometers cubed. To change it to meters cubed, remember 1 meter cubed. 1 meter is 100. 1 kilometer, not 1 meter. 1 kilometer is 1,000 meters. So if it is 1 kilometer cubed, it will be 1,000 meters cubed. So this will be times 10 power 9 to change it to meters cubed. Then this is over. Remember, I'm still getting the gradient. I'm finding the gradient. So on the x-axis, I have this 0.1. I have also this is 0.35. This is 0.35. So I'm saying 0.35 minus 0.1. Then times, note that this is t squared alone when it is in days, but I have to change it into seconds. Remember, 1 day, not squared, just 1 day, is in seconds, it will be 24 hours times 3,600. That is 1 day. But note that this is in days squared. So 1 day squared is going to be this squared. So here I will multiply this by 24 times 3,600, where this must be squared to change it to seconds squared. So then this one is seconds squared. I am pressing, why can't I just substitute and find m? So I make it m the subject here, but I will press the calculator. 4.5 minus 1.3 exponent 23. Divide by open bracket 0.35 minus 0.1, 24 times 3,600 squared. This one I multiply the answer by 4 pi squared times 4 pi squared. I now have times 4 pi squared. Again, I divide the answer because I'm making m the subject. So m is going to be equal to, say, 2.155 times 10 power 15 divided by g, which is 6.67 times 10 power negative 11. I think the power becomes 26. So I am getting 1.01 times 10 power 26. I can press this again and I see 4.5 minus 1.3 1 exponent 23. sorry, this is 1 point. This is 1.715 times 10 power 14. Let me check again. Divide by 6.67 exponent negative 11. Why isn't how did I get this? Okay, so I was not multiplying with 4 pi squared. Sorry. I said you watch the lesson until the final answer is written so that you now know what to do. So this is 6.769 times 10 power 15 divided by 6.67 exponent negative 11. Yeah. So normally I don't want to write subsequent answers. That's why it confuses me a lot. I want to just press the calculator once. So for those who are good at mathematics, that is fine. But there are those friends of mine who are PCB students. For you can't use, even converting here becomes a challenge. And if that is the case, as long as you know that the gradient is gm over 4 pi squared, you can also use the expression as it is. After all, they didn't say use the gradient. You can still use the expression as it is directly. And if that is the case, it means m is going to be equal to 4 pi squared x cubed divided by gt squared. But you must be careful when you are substituting. You must be very careful when you are substituting. So this will be 4 pi squared times. Where there is x, I will choose a value for x for x cubed. I will choose a value for x cubed. Let me just take maybe which one should I take that is easy to compute. Okay, I can take 3.2. 3.2 times 10 power. Of course, the power, this is power 14 in kilometers cubed, so we must again add power 9. So this will be times 10 power 14 times 10 power 9, change it to meters cubed, divide by g, which is 6.67 times 10 power negative 11 times t. So the period corresponding to 3.25, 3.2 is 0.25. So this is 0.25, so I will say 0.25. Remember, this is in days squared, so you have to change it again to seconds squared. So this becomes 24 times 3,600. Again, it is also squared. It will give you the same answer, 0.01 times 10 power 6. You can verify. You can always verify. So you can just choose a point from the graph and substitute correctly, but remember the conversion in SI units to arrive at kilograms. A satellite of mass ms is in a circular orbit of radius x about the Earth. The Earth may be considered to be an isolated uniform sphere with its mass m at its center. Show that the kinetic energy Ek of the satellite is given by that expression. So first of all, they said explain your working. We know that the gravitational force provides the centripetal force. The gravitational force provides the centripetal force. And if that is true, we shall have that G capital M small m over x squared is going to be equal to m v squared over x. So multiply both sides. We multiply both sides by half. You can multiply both sides by a half. If you multiply both sides by a half, note that x has cancelled out. This one has cancelled with that. Multiplying both sides by a half, I have that g m over x, this side is times a half, is equal to a half m v squared. Okay, so a half mv squared is kinetic energy, so it means Ek is going to be capital G, capital M. By the way, this was called ms over 2x. This is ms, meaning mass of the satellite. So that is the expression for kinetic energy. Just equate gravitational force to centripetal force, multiply both sides by a half, and come up with the expression for kinetic energy. State an expression in terms of G, capital M, and ms, and x for the gravitational potential energy EP. Why can't I go back to the normal size? Okay. So we know that potential energy is equal to mass times potential, but potential is always negative, so this becomes m. Negative, I mean. So potential energy EP is going to be equal to the negative of capital G, capital M, divided by x, that is potential, times ms, that is the gravitational potential energy. This is m subscript s. It is m subscript s. It's not m times s. Using answers from 1 and 2, derive an equation for the total energy. So total energy, E total, is simply E kinetic plus E potential. E kinetic is capital G, capital M, small ms over 2k, 2x. That was kinetic, plus potential is negative G m ms over x. LCM is, I think, 2x. When you add these two, 2x by that gives you G m ms minus. This by that times that gives you negative 2 G m ms. When you subtract G m ms minus 2, you get negative G m ms over 2x. So this is the expression for the total energy. That's the expression for the total energy. Small resistive forces acting on the satellite causes the radius of its circular orbit to change. That is, of course, resistive forces will automatically cause the radius to decrease. So I'll start from here. This one decreases because they said use your answers in A to state for the satellite whether each of the following quantities increases, decreases, or remains constant. Resistive forces will cause the radius of orbit to change because after all, total energy is wasted to overcome the force of resistance, so total energy decreases. If you don't want to do it that way, you can think about the expressions themselves. Because total energy decreases, the radius of orbit decreases. What happens to the potential energy? You go to the expression. When x becomes smaller, this value becomes bigger, but because of the negative, a big negative number is smaller than a small negative number. So we say potential energy decreases. If you want to look at kinetic energy, note that kinetic energy is positive. Ek is equal to G m ms over 2x when x decreases. If x becomes smaller, it means this becomes bigger. And since it is positive, so kinetic energy increases. Simple logic. I said for potential energy, because potential energy is negative G m ms over x. When x decreases, it means this value here becomes bigger. But because of the negative, a bigger negative number is smaller than a small negative number. That's why we said potential energy decreases. Okay, next. State Newton's law of gravitation. Sorry for that. So Newton's law of gravitation. The force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation. Note that this force is always attractive. So I can even say the gravitational force of attraction, just to change slightly. The gravitational force of attraction between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. Okay, so that is Newton's law of gravitation. Again, this same question has come. The planet Neptune has 8 moons. Each moon orbits Neptune in a circular path of radius r with a period t. Assuming that Neptune and each moon behave as point masses, show that r and t are related by that expression. Mn is the mass of Neptune, and its moon, let the mass of the small moons be small m. So we know that the gravitational force provides the centripetal force. And if this is true, capital G, capital Mn times small m over r squared is going to be m v squared over r. And do not forget, v is equal to omega times r, which is the same as 2 pi over t times r. So small m has cancelled, small r has reduced to that. So we remain with the capital G, capital M, n over r being equal to, where there is v squared, I'm substituting, so it becomes 4 pi squared r squared over t squared. Then we cross multiply. When we cross multiply, hence we have that G mn is 4 pi squared r cubed over t squared. Data for the moon Triton that orbits Neptune, and for the moon Oberon that orbits the planet Uranus are given in the table below. Use the expression in B to determine the ratio mass of Neptune over mass of Uranus. Okay, for those who are poor at math, you can find the mass of each using the above expression and then divide. For us who are good at math, we are just going to come up with two equations and divide them. So I will say G times mass of Neptune is equal to 4 pi squared radius around Neptune cubed divided by period around Neptune squared. Divide by, so here I'm now again dividing by another equation considering a Uranus. This would be G times the mass around of Uranus over this side I will have 4 pi squared radius of orbit around Uranus cubed divided by period of Uranus squared. When you simplify this, do note that G has cancelled, 4 pi has cancelled. Period of Uranus goes up. So you have period of Uranus over period of Neptune, and these ones are raised power 2 times radius of Neptune over radius of Uranus, these are raised power 3. So that is mass of Neptune over mass of Uranus. We substitute. When I substitute, I know that when I consider a period, they are all in days, so that is 13.5 over 5.9, and this is squared times. I will not consider this power because they all have the same power and I'm dividing. So I'll just take Neptune, which is 3.55 over Uranus, around Uranus, which is 5.83, but this is raised power 3. I press my calculator. So I am getting 1.18. So the ratio is 1.18. I know some people prefer to write 2 to 3, 1 to 7, and so on, but that's already a ratio. The Earth may be considered to be a uniform sphere of radius this, with its mass given as that, concentrated at its center. The Earth spins on its axis with a period of 24 hours. A stone of mass 2.5 kilograms rests on the Earth's surface at the equator. Calculate, using Newton's law of gravitation, the gravitational force on the stone. So gravitational force, that is force due to gravity, is capital G, capital M, small m over r squared over x squared. So this is going to be 6.67 times 10 power negative 11 masses 5.98 times 10 power 24, then 2.5 divide by the radius because it is on the surface. So this will be 6.37 times 10 power 3. Oh, it is in kilometers, so this becomes again times 10 power 3, and this should be squared. Calculator. So from my calculator, I am getting 24.6 newtons. So this is 24.6 newtons. Then determine the force required to maintain the stone in its circular path, that is centripetal force. Centripetal force is equal to mv squared over r, which is equal to m omega squared r, which is equal to m into 2 pi over t, this is squared, times r. So that is m 4 pi squared over t squared times r. We substitute. Mass is 2.5 times 4 pi squared times r, which is 6.37 times 10 power. That would be power 6 because it was in kilometers. Divide by, they said 24 hours as the period, so that is 24 times 3600, and that should be squared. So to three significant figures, I am getting this as 0.0842 newtons. Okay, then the stone is now hung from a Newton meter. Note that there is centripetal force, there is gravitational force. The stone is now hung from a Newton meter. Use your answers in Roman 1 to determine the reading on the meter. Give your answer to three significant figures. So the reading on the meter will be the resultant force on the mass. So the reading is going to be 24.6 minus 0.0842. And this is giving me 24 point, what is that? That is 24.5. So to three significant figures, it is 24.5 newtons. A satellite is orbiting the Earth. For an astronaut in the satellite, his sensation of weight is caused by the contact force from his surrounding. The astronaut reports that he is weightless despite being in the Earth's gravitational field. Suggest what is meant by the astronaut reporting that he is weightless. A satellite is orbiting the Earth. For an astronaut in the satellite, his sensation of weight is caused by the contact force from his surroundings. The astronaut reports that he is weightless despite being in the Earth's gravitational field. Suggest what is meant by the astronaut reporting that he is weightless. That is very easy. Every time we have been seeing that it is the gravitational force which provides the centripetal force. And if the astronaut gets an impression that he is weightless, it's only because the gravitational force is balancing with the centripetal force, or the centripetal force is balancing with the gravitational force. So that means the resultant force would be zero, giving him a sensation that he is weightless. Very simple. So we said the gravitational force provides the centripetal force. The gravitational force provides the centripetal force, and the gravitational force could be equal or is equal to the centripetal force. The gravitational force is equal to the centripetal force, and it means the sensation of weight or the contact force is going to be the difference between Fg and Fc, which is 0. Or the weight on the person will be the difference between the two forces. So let me say the sensation. What is sensation? Sensation. The sensation. This spelling is not good for me. The sensation of weight. The sensation of weight is the difference. Is the difference between the gravitational force and the centripetal force, which is 0. So if the difference between the gravitational force and the centripetal force is 0, then you get an impression that you are weightless. Okay. State Newton's law of gravitation. The force or the gravitational force of attraction between 2-point masses is directly proportional. I'll simply say the force between 2-point masses is directly proportional. Is directly proportional to the product of the masses and inversely. The inversely proportional to the square of their separation. Okay, so that is Newton's law of gravitation. Planets have been observed orbiting a star in another solar system. Measurements are made of the orbital radius r and the time period t of each of these planets. The variation with r cubed of t squared is shown. So here they have shown the variation of r cubed with the t squared. The relationship between t and r is given by that expression there, where g is the gravitational constant and m is the mass of the star. Determine mass m. I think this is easy. I just make m the subject. So m is going to be equal to 4 pi squared r cubed divided by g t squared. For those who are not good at math, you can just substitute. Go to the graph, find values of t squared and r cubed. R cubed is in SIns, there is no problem with that. So we shall not need to change. But t squared is in years squared. So it means if we want it in seconds squared to be able to get mass in kilograms, we shall change from years squared to seconds squared. Remember, 1 year is 365 days times 24 hours times 3,600 in seconds. Now, if it is 1 year squared, it will be this one squared, turn it seconds squared. Okay, so I will take a point. Let me take r cubed as. Let me take. Why can't I take the last value of r cubed? It is easier for me. 1.2 here 1.12345. So that is 2.4. So I'm taking the last value of r cubed with its corresponding value of t squared. So this is going to be 4 pi squared times 1.2 times 10 power 34 on the x-axis, divided by 6.67 times 10 power negative 11. Then for t squared, t is 2.4 from the graph, 2.4 times, I have to change, this is in years squared, so I have to change the other one, the units, to seconds. So this will be 365 days, 24 hours, 3600 seconds, and that is squared. My calculator. So I am getting 3.0 times 10 power 30. 3.0 times 10 power 30 kilograms. You can also verify. Part C. A rock of mass m is also in orbit around the star in B. The radius of orbit is r. Explain why the gravitational potential energy of the rock is negative. This is a common question. We have explained it. First of all, we said potential at infinity is defined to be zero. The force between two masses is always attractive. So when the masses are moved apart, it means work is done against the force of attraction. So energy is gained. When the masses come closer or move towards each other, or when a mass comes from infinity, work is done out of the mass, or work must be done on the mass to move it to infinity. So you can explain either way. Either way would be correct. So we are saying potential energy at infinity is defined to be zero. Potential energy at infinity is defined to be zero, and the gravitational force is always attractive. The gravitational force is always attractive. So when you move an object to infinity, it gains energy. If you move it away from infinity, it loses energy. So the energy will always be less than zero, because at infinity it is zero. Moving it to infinity, you'll be moving it through negative values before it reaches zero. Moving it from infinity, you'll be moving it to negative values from zero. So we are saying work must be done on the rock. Work must be done on the rock to move it to infinity. So that work done must be negative because it should be less than zero. Or energy is lost when an object comes from infinity, or potential energy decreases when an object comes from infinity to a certain point. Show that kinetic energy Ek of the rock is given by that expression. First of all, we know that the gravitational force provides the centripetal force. The gravitational force provides the centripetal force, capital G, capital M over r squared is equal to m v squared over r. Small m, okay, since we want m there, r has reduced that. Multiply both sides by a half, so a half times capital G small m over r is equal to a half times mv squared. But a half times mv squared is kinetic energy, so Ek is going to be equal to g m over 2r. As simple as that. Use the expression in serum to derive an expression for the total energy of the rock. Use the expression. We know the expression for kinetic energy. All that we don't have is potential energy. Note that potential energy is mass times potential, and potential is always negative. So this gives us negative capital G capital M over small m over R. Let me use a small r here for uniformity. So potential energy is given by that. And total energy E total, which I'll call E T, is sum of E kinetic plus E potential. E kinetic is capital G M small m over 2r plus negative capital G M over R. LCM is 2r. 2r by that is G M minus, that is twice G M. So this gives you negative G M over 2r as the total energy. The Earth may be assumed to be an isolated uniform sphere with a mass of that concentrated at its center. A satellite of mass 1,200 kilograms is in a circular orbit about the Earth in the Earth's gravitational field. The period of the orbit is 94 minutes. Define gravitational field strength. We said gravitational field strength G is the force acting on a unit test mass placed in the field. So this is simply force per unit mass. The force acting on a unit test mass placed in the field, force per unit mass. If you want, you can add acting on a small test mass placed in a gravitational field. This is basically of a large mass. The force experienced by a unit test mass placed in the region of the gravitational field of a larger mass. That is the gravitational field strength. Calculate the radius of the orbit of the satellite. The Earth, a satellite of that is in a circular orbit about the Earth. Okay. Remember, gravitational force provides centripetal force. So I'll simply say gravitational force Fg provides centripetal force Fc. And if I equate the two, capital G, capital M, small m over r squared is equal to mv squared over r. Small m has cancelled, small r has cancelled. Remember, v is equal to omega r, which is 2 pi r over t. So we now have that G capital M over small r is equal to, I am substituting 4 pi squared r squared over t squared. So I am now going to just cross multiply and substitute. So you notice that I have G is 6.67 times 10 power negative 11. Capital M is given as 6.0 times 10 power 24. Should be equal to 4 pi squared times r cubed divided by t. I've multiplied this by this to get r cubed. And the t, They have given us, I think, 94 minutes. So T will be 94 times 60, and this should be squared. 94 times 60, that should be squared. So we make r cubed. I'm just going to cross multiply and divide by 4 pi cubed and find the cube root. So I have cross multiplied and divided by 4 pi squared, and I've found the cube root. And my answer is 6.9 times 10 power 6 as r. Remember to find the cube root. Part C, rockets in the satellite are fired so that the satellite enters a different circular orbit that has a period of 150 minutes. The change in the mass of the satellite may be assumed to be negligible. Show that the radius of the new orbit is 9.4 times 10 power 6. The period is 150 minutes. I think that is very easy. I'll just quote the same expression I have above, that G m t squared over 4 pi squared is equal to r cubed when you make r cubed the subject. So the period has changed. So we shall have 6.67 times 10 power negative 11. Of course, the mass of the earth is not going to change. Power 24 times the new period is 150 times 60, and that is squared, divided by 4 pi squared. I'm just going to find r straight away. I will find the cube root because there are only two marks. This is 150. Okay, so pressing the calculator, I'm finding r as 9.4 times 10 power 6 in meters. State with the reason whether the gravitational potential energy of the satellite increases or decreases. So you notice that we have moved from 6.9 to 9.4. Gravitational potential energy is given by negative G m over r. So when r increases, this quantity here becomes smaller. A negative smaller number means an increase. So we are saying the separation increases. The separation increases. And if that is true, so it means potential energy. So potential energy increases. Alternatively, you can think about it as movement against gravity, against gravitational force. For example, you can say movement is against. The movement is against gravitational force. So potential energy increases. Whenever you go against the gravitational force, the gravitational potential energy increases. That is self-explanatory. Next, determine the magnitude of the change in the gravitational potential energy of the satellite. Determine the magnitude of the change of the gravitational potential energy of the satellite. So potential energy, remember, is equal to negative G capital M small m over r. Now the change, we shall get the highest minus the lowest. Capital G, capital M small m will remain constant. What is changing is r. So I pulled these ones out of the bracket by substitution. 6.67 times 10 power negative 11, that is capital G. Capital M is the mass of the Earth, 6.0 times 10 power 24, it has not changed. Then M is still 1,200, but we have 1 over R. So because we are getting the highest minus the lowest, the highest potential energy is at a higher value of R, and the lowest potential value of energy is at a lower value of R. So when I say remember this is negative. So when I say R1 is the lowest and R2 is the highest, when I subtract it, it becomes, if I say negative 1 over R1 minus negative 1 over R2, note that, no, R2 minus R1, note that R2 is the highest. Because of this becomes positive, so it ends up becoming 1 over R1 minus the smallest value of R minus the largest value of R. So this will be 1 over 6.9 times 10 power 6, which we got before, minus 1 over 9.4 times 10 power 6 that we got before, that we got up there. Alternatively, you can substitute. You get potential energy at this distance. You also get potential energy at this distance, and you subtract. Remember, potential energy will be negatives, but when you subtract, the answer will become positive because you get the highest minus the lowest. So from my calculation, I'm getting 1.9 times 10 power 10. You can also verify. Define electric field strength without wasting time. Field strength is force per unit mass. And so on and so forth. The force per unit mass acting on a small test mass placed in a gravitational field. So that is gravitational field strength. Then an isolated planet is a uniform sphere of radius 3.39 times 10 power 6. Its mass is 6.42 times 10 power 23 kilograms. May be considered to be a point mass. A point mass constituted at its center. The planet rotates about its axis over a period of 24.6 hours. For an object resting on the surface of the planet at the equator, calculate 3 significant figures. The field strength, gravitational field strength, that is G, small g is capital G, capital M over R squared, 6.67 times 10 power negative 11 times 6.42 times 10 power 23. The radius is 3.39 times 10 power 6, and this is squared. 3 significant figures. So this is 3.73 newtons per kilogram. Then again to 3 significant figures, calculate the centripetal acceleration. Centripetal acceleration. So since we said centripetal force is equal to mass times v squared over r, comparing with ma, This means that centripetal acceleration is equal to v squared over r. And remember, v is equal to omega times r, and which omega is 2 pi over t. So v is omega 2 pi over t times r. Okay, so I'm now simplifying this. So the centripetal acceleration s is going to be, it will be v squared, which is this, 4 pi squared r squared over t squared, then divide by r. So it will be times 1 over r. So 1 r cancels with the square. And you get 4 pi squared over t times r. When we substitute, 4 pi squared times r is 3.39 times 10 power 6, I think, divide by t. By the way, this is t squared. This r here cancelled with the square. So t was 24.6. 24.6. It was in hours, so times 3,600, change to seconds, but is squared. I'm pressing my calculator. So to three significant figures, this is 0.0171. The force per unit mass exerted on the object by the surface of the planet. The force per unit mass exerted. So remember, gravitational field strength was the force per unit mass. Then the centripetal acceleration is also the force per unit mass. Therefore, the resultant force per unit mass is going to be the difference between these two. So this is going to be, so the force per unit mass is going to be the difference. Force per unit mass is going to be 3.73 minus 0.0171. The resultant force per unit mass is going to be the difference, which is 3.71. So that will be the force per unit mass. Somebody may be wondering, how does the acceleration become force per unit mass? Gravitational field strength is force per unit mass. If this is 1 kilogram, then this is the same as that in magnitude. Okay. Next, define gravitational potential. This is the work done. The work done in moving a unit mass from infinity to a point, from infinity to a point, or to the point, to be clear. Work done moving a unit mass from infinity to a point, or to the point in the gravitational field. TESS is a satellite of mass 360 kilograms in a circular orbit around the Earth, above the Earth, as shown. The radius of the Earth is that. Radius of the Earth is given, and the mass of the Earth is considered to be a point mass at its center. It takes TESS 13.7 days to orbit the Earth. Show that the radius of orbit of TESS is 2.4. Remember, gravitational force provides centripetal force. By the way, may I run through the questions very fast, but you need to sit down and study the questions very carefully. Gravitational force provides centripetal force. So centripetal force is given as mv squared over r. Gravitational force is G, capital M, small m over r squared. Do not forget, V is omega r, which is 2 pi over T times r. So I'm going to, small m has cancelled, small r has reduced. So it means 4 pi squared r squared over T squared is going to be G m over r. I'm going to make r the subject because we want the radius of orbit. So r cubed is going to be equal to G m T squared over 4 pi squared. I'm now substituting 6.67 times 10 power negative 11, 6.0 times 10 power 24 for the mass, times the period is 13.7, so 13.7 times 24 times 3600, and that is squared. The whole of this is divided by 4 pi squared. So press your calculator and find r cubed. So r cubed is approximately 1.3824 times 10 power 25. You can now find the cube root of the answer to get approximately 2.4 times 10 power 8 meters. You can verify. Part 2. Calculate the change in gravitational potential energy between TESI in orbit and TESI on a launch pad on the surface of the Earth. So we have in orbit, where the radius of orbit is that, and we have the surface of the Earth, where the radius is, where r is the radius of the Earth. Okay, so potential energy is equal to negative capital Gm small m over r. Gm and small m will be constants. So the work done to move, because we want the change, so the change in potential energy is going to be the work done. So I'll say the higher orbit is r2, so this will be negative G m over r2 minus the lower orbit, which is negative G m over r1, which implies that I will simply have G m into this becomes positive this side, so it is 1 over r1 minus 1 over r2. So we get the lower orbit minus 1 over the higher orbit. So this is going to be equal to 6.67 times 10 power negative 11 multiplied by 3600 multiplied by 6.0. No, this is 360. 360. 6.0 times 10 power 24 divide by, no, times 1 over the lower orbit, which is the radius of the Earth, 6.4 times 10 power 6 minus the higher orbit, which is 2.4 times 10 power 8. I'll press the calculator just directly. So I'm getting 2.2 times 10 power 10 joules. You could also use the first one, find potential energy at the surface, find the potential energy at this value here, R is equal to 0.4 times 10 power 8 and subtract. Of course, potential energy at a higher orbit, although it is negative also, it is bigger than potential energy at a lower orbit. So you get higher minus lower, where the answer will be positive. Use the information in B Roman 1 to calculate the ratio gravitational field strength on the surface of the Earth over gravitational field strength at a location of Tessie in orbit. So we are finding small g. Small g is equal to capital G m over r squared. Now that we are experts, I know g on the Earth's surface will be equal to capital G m over r, radius of the Earth actually, squared. And g at the position of Tessie will simply be capital Gm over radius of orbit of Tessie, r Tessie squared. So we want the ratio, we divide. When we divide, Gm cancels and this becomes the reciprocal. So it means the ratio is going to be equal to Ge, G on the surface of the Earth divided by this. This goes up, r of Tessie over r of the Earth. But remember, these ones are squared. You get the reciprocal when you divide this by that. This one goes up. So when we substitute, this will be 2.4 times 10 power 8. That's the radius of orbit of Tessie over 6.4 times 10 power 6. That is on the Earth, but this is squared. Pick your calculator. So this is 1,400 to two significant figures. State what is meant by a field of force. We say the field of force is a region of space where a particle, an object, experiences a force. A region of space where a particle experiences a force. That is a field of force. Don't be specific because they have not specified the gravitational field of force. They have not specified electric or magnetic, so it is just general. A region of space where a particle or a body experiences a force. And the gravitational field strength, that is G, is force per unit mass. So this is force per unit mass. The force acting on a small test mass, on a unit test mass placed in a region of the gravitational field. An isolated planet is assumed to be a uniform sphere of radius 3.39 times 10 power 6 meters, with its mass given as that concentrated at its center. Calculate the gravitational field strength at the surface of the planet. So gravitational field strength G is capital Gm over r squared, 6.67 times 10 power negative 11 times 6.42 times 10 power 23 divided by the radius 3.39 times 10 power 6, and this is squared. Answer. So this is giving me 3.39 0.73 newtons per kilogram. Calculate the height above the surface of the planet in B at which the gravitational field strength is 1.0% less than that of its value at the surface of the planet. So that means the gravitational field strength at that height, G at the height, is going to be, because it's 1.0% less, so it becomes 100 minus 1 divided by 100 of 3.73. I think that is true. So this becomes 0.99 of 3.73. That is the value of G at height h. So we want to find the height h. So remember, G is given by capital G, which is 6.67 times 10 power negative 11 times capital M, 6.42 times 10 power 23, divide by, you find the radius of orbit. So this will be, okay, I'll just find R squared. We are substituting in G equals to capital G M over R squared. So I first find R. So I find R squared, then I find the square root. So this is giving me 3.41 times 10 power 6 in meters as R. Then the height h is going to be R minus the radius of the planet. The radius of the planet was given as the radius of the planet 3.39 times 10 power 6. So this is 3.41 minus 3.39 times 10 power 6. So this is giving me 2.0 times 10 power 4 meters. Define gravitational potential, the work done in moving a unit mass. Work done in moving a unit mass from infinity to the required point in the gravitational field. Okay. The Earth may be considered to be a uniform sphere of radius 6.4 times 10 power 6 meters, mass 6.0 times 10 power 24 kilograms, concentrated at its center. A satellite of mass 2.4 times 10 power 3 kilograms is launched from the equator. It is placed in an equatorial orbit at a height of 5.6 times 10 power 6 meters above the Earth's surface. Calculate the change (EP) in gravitational potential energy of the satellite for its movement from the surface of the Earth to its position in the equatorial orbit. Surface of the Earth to its position in the equatorial orbit. Note that it is placed in equatorial orbit at this height, so it means the radius of the equatorial orbit is going to be the sum of these two. That is 6.4 plus 5.6 times 10 power 6. I think this is 1.2. 1.2 times 10 power 7 meters. When you add those two, you can check 1.2 times 10 power 7. So we are now going to find the change in potential energy. So note that the change in gravitational potential energy is the mass times the change in the gravitational potential. And the gravitational potential energy is negative mgh. Gravitational potential energy is negative m, not mgh, negative capital G m small m over r. So it means the change in potential energy is going to be, we get higher orbit minus the lower orbit, but remember it is negative, then it comes lower orbit minus higher orbit. So I'm simply substituting G is 6.67 times 10 power negative 11. Capital M is 6.0 times 10 power 24. Small m is 2.4 times 10 power 3 times 1 over r, change in r. R is the one which is changing. So we shall get 1 over the lower orbit, which will be the surface of the Earth, that is 6.4 times 10 power 6 minus 1 over the higher orbit, which is actually 1.2 times 10 power 7. I know some people, when I say higher orbit, lower orbit, they must be confused. The change in potential energy, this is for those who don't understand mathematics very well. So we are getting the change in potential energy as negative G, capital M, small m over, we are getting the higher orbit, I'm calling it R2, minus negative G, capital M, small m over the lower orbit, which is R1. Because this becomes positive, this becomes capital G, capital M, small m over R1 minus capital G, capital M, small m over R2. This was, remember, the lower orbit. This is now the higher orbit. This is the surface of the Earth. This is when it is at a height. So I will press the calculator just once. So pressing the calculator, I am getting 7.0 times 10 power 10. 7.0 times 10 power 10. You can verify. Determine the speed of the satellite. Determine the speed of the satellite. If the gravitational potential in the force due to gravity provides a centripetal force, we can determine the speed of the satellite. If Fg provides Fc, then capital G, capital M, small m, r squared, mv squared over r. So v squared is equal to capital G, capital M over r. One r here cancels with that, small m cancels. So this will be 6.67 times 10 power negative 11, 6.0 times 10 power 24. R is 1.2 times 10 power 7 when it is in orbit. So from my calculator, I get 5,800 to two significant figures. Before the satellite in B is launched, its speed at the equator due to the Earth's rotation is 470 meters per second. Suggest why the energy required to launch the satellite depends on whether the satellite in its orbit is traveling from west to east or from east to west. That is very simple. The Earth rotates from west to east. So if the satellite is launched the other way around, then a different amount of energy is going to be required. So they said suggest. So you can give many. There are many suggestions. I will just give a few. Suggest why the energy required to launch the satellite depends on whether the satellite in its orbit is traveling from west to east or from east to west. If it's traveling from west to east, it is most likely going to be in a geostationary orbit. So it will require a different amount of energy. So one, the Earth's rotation is from west to east. The Earth's rotation is from west to east. Or you could say the satellite is already moving west to east, because here they said it is in equatorial orbit. And where is it? Okay, it is above the equator. So it is already rotating west to east. So the Earth's rotation is from west to east. So this also determines the energy of the satellite. And if the Earth's rotation is from west to east, if it is launched from west to east, it will require a smaller amount of, or there will be a smaller gain in energy. A smaller gain in energy is going to be required if orbit is west to east. A smaller gain in energy will be required if the orbit is west to east. After all, the Earth is already rotating west to east, so you need a small amount of energy to put a satellite into motion west to east. Or small gain of energy, small gain in energy is required if the orbit is in the same direction as the rotation of the Earth. Or if instead of saying smaller gain in energy, you can also talk about smaller change in velocity if the orbit is west to east. All these imply the other. Or smaller change in velocity. You need a smaller change in velocity if the orbit is west to east. If the orbit is east to west, then there will be a smaller change, a greater change in velocity. Then state what is meant by gravitational force. I think that is the weight. Gravitational force. Some people may fail to define gravitational force. That the force between two masses is the gravitational force. The force acting between two masses, or the force on one mass due to another mass, is the gravitational force. The force on a mass due to another mass. The force on a mass due to another mass, or the force between two masses. The force on a mass due to another mass, or the force between two masses. That is the gravitational force. Binary star. A binary star system consists of two stars, S1 and S2, each in a circular orbit. The orbit of each star in the system has a period of rotation t. Observations of the binary star from Earth are represented in the figure. So let me try to minimize this so that this comes onto one page. Okay, so observations have been represented there. So we start from the vertical at t equals to 0, horizontal t equals to a quarter period, t equals 3/4, t is equal to half a period, and after one complete period, we are back to where we started from. Okay. Observed from the Earth, the angular separation of the centers of S1 and S2 is 1.2 times 10 power negative 5 radians. Angular separation of the centers. So that is going to be theta or delta theta. Angular separation or angular displacement between the two centers is delta theta, observed from the Earth. So this view here is observations of the binary star from the Earth are represented like that. But observed from the Earth, the angular separation of the centers of S1 and S2 it's like they appear to be the imaginary line between them is appearing to be at an angle which we are calling 1.2 times 10 power negative 5 radians. The distance of the binary star system from the Earth is this. So this is the angle when observed from the Earth. Let me try to put the Earth somewhere here. So let's say this is when observed from the Earth. The distance of the binary star system, so the average distance of the star system from the Earth is 1.5 times 10 power 15 meters. State the separation D of the centers. So state D. So we are going to state D of the centers of S1 and S2. So if D is like the arc length and theta is the angular displacement, then we know from angular displacement is going to be the arc length S over R. Since this is in radians, so S is equal to R times delta theta. So the distance D is going to be R times the separation of the the angular displacement. So which will be 1.5 times 10 power 17 times 1.2 times 10 power negative 5. Answer. So this is giving me 1.8 times 10 power 12. As simple as that. The stars S1 and S2 rotate with the same angular velocity omega about P. The stars rotate with the same angular velocity omega about P, so omega is the same as illustrated in the figure below. So they are rotating about P. First of all, they experience a force of attraction between them, which is the same, equal, but opposite. And that force is the one which provides the centripetal force. That means the centripetal force of the two stars must be the same. But remember, centripetal force is towards the center and it is towards point P because they are rotating about point P. Okay, calculate the angular velocity omega. So omega is equal to 2 pi. I can modify this. Omega is 2 pi over t. 2 pi over t. So this is 2 pi divided by the period is 44.2 years. 44.2 times 365 days times 24 hours times 3600. Pressing my calculator to get omega. So omega is 4.5 times 10 power negative 9. As simple as that. By considering the forces acting on the two stars, show that the rotation of the masses of the star is given by The ratio of the masses of the stars is given by that, considering the forces. First of all, the force between two masses is equal but opposite, so the gravitational forces are equal. And remember, gravitational force is the one which provides the centripetal force, so the centripetal forces are also equal. So gravitational force the gravitational forces are equal. So centripetal forces about P are the same, because it is the gravitational force which provides the centripetal force. And we know that centripetal force Fc is equal to mv squared over r, which is the same as m omega squared r. R is the distance from the center, or from one center to another center. So let's consider sphere S1, star S1. So for S1, the centripetal force is going to be M1, that is capital M1 omega squared. Omega is the same. The distance of sphere S1 is x from the center, so that is x. This should be equal to the other one. If this is x, this distance here must be equal to d minus x, because the separation of the the stars is d. Okay? So the other one will be m2 omega squared into d minus x. So omega cancels. So m1 divided by m2 is going to be equal to d minus x over x as required. The most important point is this one here, this part here. The gravitational forces are the same, because the force between two masses, the equal proportion to the product of the masses. It will be equal but opposite. And it is the gravitational force which provides the centripetal force. So the centripetal force is about P will also be the same. Okay. They have also told us that the mass m1 of star S1 is given by that expression. They have also told us the ratio in part 2, that is m1 over m2, which is d minus x over x, is equal to 1.5. Okay. Use data from B and your answer in C to determine the mass m1. So we are having that d minus x over x is equal to 1.5, because they say the ratio m1 over m2 is 1.5, so this is true. And that means when I sort of simplify it, so it is 1.5x is equal to d minus x. When I correct like terms, 2.5x is equal to d. Or I make x the subject, x is going to be 0.4d. In other words, it is dividing both sides by 2.5, I get 0.4d. So that is x. Then I think that is all. We just substitute. So I make m1 the subject here. m1 is going to be d squared. m1 is going to be d squared, which is d squared into d minus, where there is x, I put 0.4d. 0.4d omega squared divided by this value of g here, divided by g. We are now substituting. Of course, d minus 0.4d, it becomes 0.6d, then times this d, which becomes 0.6d cubed, I guess. 0.6 d cubed, then times omega squared over capital G. So when we substitute, this will be 0.6 times omega d will be 1.8 times 10 power 12. This is now raised to power 3. D is, I hope I quoted it correctly. D was 1.8 times 10 power 12. Okay. Then times omega, I think we got omega as omega, we have calculated omega above as 4.5. So this will be times 4.5 times 10 power negative 9, but this is raised to power 2. It is raised to power 2. Then divide by 6.67 times 10 power negative 11. So you pick your calculator and see what you get. From my calculator, I'm getting 1.1 times 10 power 30. The gravitational potential at a point is what we want to define. Gravitational potential at a point. So this is something you are now very familiar with. The work done per unit mass in moving a unit mass from infinity to the point. So this is work done in moving a unit mass from infinity to the point. An isolated solid sphere of radius r may be assumed to have its mass concentrated at its center. The magnitude of the gravitational potential at the center of the sphere is phi. So that means at the center, no, not at the center, at the surface is phi. Note that the radius is r, so the surface is here along r. This is where we have the surface. On the figure, show the variation of gravitational potential with distance. So remember, potential is equal to negative G capital M over the distance from the surface. So it is going to be a negative below the x-axis. On the surface, it is just phi. So our graph starts at this point here. So we can check what is happening at 2 phi. So what is phi at 2r, not at 2 phi? So this will be negative G M. By the way, this is negative G M over r. This is at r on the surface. At 2 phi, this will be over 2r, which is the same as a half of the first value of phi that we obtained. Then for the other one, phi at 3r will also be a third of the first value of phi. Phi at 4r will be a quarter of the value of phi that we obtained. So we plot those points. So at r it is just phi. At 2r is a half phi, which is this point here. Hope that is the point. 2r, it is 0.5 phi. Then a third r, because the scale is 0.05, just say a third divided by 0.05. A third divided by the scale of 0.05. That is the value of one small square. This is giving me 6.6 small squares. That is approximately 7 small squares from the origin. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, around here. that is where we have a third of phi. Then at quarter, that is 0.25, which is a half of this. I count only 5, 1, 2, 3, 4, 5 here. So my graph will go through these points. A smooth curve. So it could be better than me drawing a very smooth curve. This one is this one. This is 0.25 of phi. So you can draw a better curve. Oh, mine is not touching here, which makes it not correct. At 2r, it must be exactly at this point here. So it's not easy drawing on a computer. Yes. Yes. Okay. So you can draw a better one. Okay. Now coming up with it, you cannot cram the shape. All you need is to know how we arrived at it. How we arrived at it is what is very important. This one is 0.33 of phi. 0.33 of phi is around 6 point something small boxes from 0. The line should be negative because potential is always negative. The line passes through 2r and the line starts from r and negative phi. It goes into 2r and 0.5 phi. It goes into 3r and about 0.33 phi, and it stops at 4r and 0.25 phi. All these are negative. So that is the curve that we are talking about. And you notice that the gradient is decreasing because the line is becoming horizontal. Okay. The sphere in B is a planet with the radius 6.4 times 10 power 6 meters and mass 6.0 times 10 power 24 kilograms. The planet has no atmosphere, so it can't be the Earth. A rock of mass this moves directly towards the planet. Its distance from the center of the planet changes from 4r to 3r. So it is moving from a higher level to a lower level, so it means potential is decreasing. Calculate the change in gravitational potential energy of the rock. So gravitational potential energy is equal to negative G capital M divided by R times small r, M. Now, at this point, we are now experts. I know these are constants. It's only this which is changing. So we shall now get higher minus lower, but because of the negative, it is now the other way around. So this will be equal to, okay, let me just substitute. The change in gravitational potential energy is going to be negative Gm, capital M, small m, small m, over, let me get the from the higher orbit, that will be 4r minus negative capital G, capital M, small m over lower orbit, which is 3r. So this now becomes because this becomes positive, so we start with this. So it will be 6g capital M small m. There's a common factor of r, so I'll put it outside. 1 over 3 minus 1 over 4. When I substitute, I will have 6.67 times 10 power negative 11, 3.4 times 10 power 3, divide by, the radius is, this is 6.4 times 10 power 6, then into 1 over 3 minus 1 over 4. I think that, oh, I didn't multiply by the large mass. Yeah. The large mass is 6.0 times 10 power 24. Then times 1 over 3 minus 1 over 4. Now note that this was 3r and 4r. I factored out the small r. Now pick my calculator straight away. So I'm getting 1.77 times 10 power 10, or approximately 1.8. Explain whether the rock's speed increases, decreases, stays the same. Explain whether the rock's speed increases, decreases, or stays the same. It is even by common sense you see it is moving from a higher point to a lower point. That means there is a loss in potential energy. That means there is a gain in kinetic energy. So the kinetic energy increases, it means the speed increases. So the rock loses potential energy, so it gains. So it, how am I writing so? So it gains kinetic energy. Kinetic energy, it means kinetic energy increases, so speed increases. Alternatively, you can look at it in the way of forces. Remember, the force is always attractive. The force is attractive. And if the force is attractive, and yet the rock moves towards the planet, it means the speed increases. It's like when an object leaves space to the Earth's surface, because the force between the Earth and that object is always attractive, the object will be accelerated towards the Earth's surface, so the speed increases. So the rock, and the rock moves towards the planet, so it speeds up. It would only slow down if it was moving in the opposite direction. Okay, oh, we are almost getting done. We are remaining with a few pages. So Newton's law of gravitation, the force between 2 point masses. is directly proportional to the product of the masses and inversely proportional to the square of their separation. That is Newton's law of gravitation. A geostationary satellite orbits the Earth. The orbit of the satellite is circular and the period is 24 hours. State to the other features. So we say it is above the equator. For geostationary satellite, it's above the equator. The orbit is above the equator and it is moving from west to east. It is moving in the same direction as the rotation of the Earth. The radius of the orbit of the satellite is given as that. Determine a value for the mass of the Earth. Explain your working. This is very important. The gravitational force provides the centripetal force. The gravitational force provides the centripetal force. And if that is true, capital G, capital M, small m over r squared is equal to mv squared over r. This one cancels with that. Remember, v is equal to omega r, which is 2 pi r over t. So when we substitute capital G, capital M, and this one also cancels, over r is 4 pi squared r squared over t squared. So we make a gm, we want the value of the mass. So we have 6.67 times 10 power negative 11 times the mass is equal to 4 pi squared times, when I cross multiply it becomes r cubed, so it is 4.23 times 10 power, because it is in kilometers, it becomes 10 power 7, and this is going to be raised to power 3 divided by t squared. Since it is geostationary, so the period is 24 hours, so we shall say 24 times 3600, and this is squared. And when you press your calculator, of course we know the mass of the Earth, but just to be sure, I'm making m the subject, remember. I'm simplifying this, so I will divide by 6.67 x power negative 11. So I'm getting 6.0 times 10 power 24. You have an idea about the mass of the Earth, which is approximately constant. So in calculation, you make sure you arrive at the power of 10 to be 24. Next, state Newton's law of gravitation. This is very quick. The force between 2-point masses is directly proportional directly proportional to the product of masses and inversely proportional to the square of the separation between them. Okay, the astronomer Johannes Kepler showed that the period T of rotation of a planet about the Sun is related to its mean distance r from the center of the Sun by the expression this. Where k is a constant, use Newton's law to show that the planets in circular orbits about the Sun of mass m to show that for planets in circular orbits about the Sun of mass m, the constant k is given by that. Explain your working. So when they say that part of explain your working is the easiest, gravitational force is equal to the centripetal force, provides centripetal force. So I'll simply say I'll use this space. Gravitational The gravitational force provides centripetal force. The gravitational force provides centripetal force. So I'll say capital G, capital M, small m over r squared. Did they give us r? It is r, capital R over r squared is equal to mv squared over r. So small m has cancelled out and r has cancelled that. But do not forget that v is equal to omega times r. This is capital R, which will be 2 pi over t times capital R. We substitute after squaring. So capital G, capital M over R is going to be 4 pi squared R squared over t squared. Then we cross multiply. We want to make sure that our constant is that. So we have that G M times t squared is going to be equal to or divide by 4 pi squared is equal to r times r cubed. So we notice that G m over 4 pi squared is equal to a constant. So we have now concluded that K is G m over 4 pi squared. Okay, so that is fine. Part C. A satellite is in a circular orbit about Mars. The radius of the orbit of the satellite is given as that. The orbital period is given as 2.44 hours. Use the expression in B to calculate a value of the mass of Mars. So we want to find the mass of Mars using the expression that we have just obtained above. So just pull this out. The expression that we have in B is that one there. And they have told us that the radius of the orbit is this. And the period is given as that. So we want to find the mass. So we can first of all find a constant K. Note that from the expression that we have here, K is r cubed over t squared. So I will say K is equal to r cubed over t squared, which is 4.38 times 10 power 6 over 2.44 times 2.44, it is in hours, so this would be 3,600, and this is squared. That is the constant K, by the way. And this will be equal to Gm over 4 pi. So this is equal to G, which is 6.67 times 10 power negative 11 times M divided by 4 pi squared. I'm just going to cross multiply, taking this part here. I'm dividing this. By the way, this is cubed. So I'm just dividing that. Then I multiply by 4 pi squared Then I divide by 6.67 exponent negative 11. So this is giving me m as 6.45 times 10 power 23. Define gravitational potential at a point, that is the work done. It is the work done in moving a unit, the work done moving a unit mass from infinity to a point, or to the point. The work done in moving a unit mass from infinity to the point. Then use your answer in Roman 1 to explain why the gravitational potential near an isolated mass is always negative. Use your answer. So we are using our definition. So first of all, we know that the gravitational potential at infinity is defined to be zero, and the gravitational force is always attractive. So gravitational potential at infinity, gravitational potential at infinity is defined to be zero. Gravitational potential at infinity is defined to be zero. The gravitational force is always attractive. The gravitational force is always attractive. And that means when I move from infinity, or when the masses come closer, it means the gravitational potential energy decreases. It becomes less than zero, which is maximum at infinity. So that means there is a decrease in potential energy as the masses approach, or there is an increase in potential energy as the masses move apart. So there is a decrease in potential energy as masses approach each other. In other words, when one mass moves towards another mass, work is done, or work is got out of the mass, so it loses energy. Therefore, that's why I'm saying there is a decrease in potential energy as the masses approach each other. Okay, next. A spherical planet has mass of 6.0 times 10 power 24, and the radius is given as 6.4 times 10 power 6. The planet may be assumed to be isolated in space, with its mass concentrated at its center. A satellite of 340 kilograms is in a circular orbit about the planet at a height of, so this is the height, 9.00 times 10 power 5 meters above the surface. For the satellite, show that its orbital speed is this. Remember, gravitational force Fg provides Fc. So mv squared r is going to be equal to capital G over r squared. So this one cancels, that one reduces. V is going to be equal to the square root of capital G, capital M over R, which will be the square root of 6.67 times 10 power negative 11 times 6.00 times 10 power 11, power 24, divided by R, Now the radius of orbit, this time at that height, the radius of orbit is going to be the radius of the Earth. So r is 6.40 times 10 power 6 plus 9.00 times 10 power 5, which gives you 7.30 times 10 power 6. So r is 7.3 times 10 power 6 as r. So pressing my calculator just to verify the answer. Finding the square root. Automatically it is giving me 7.4 times 10 power 3 meters per second. Then calculate the gravitational potential energy. Calculate the gravitational potential energy. Of course, gravitational potential energy is going to be the mass times the potential. Mass times the potential, but remember the potential is always negative, so this becomes negative capital G, capital M, small m over R. When we substitute, negative 6.67 times 10 power negative 11 times 6.00 times 10 power 24 times small mass was 340 divided by 7.30 times 10 power 6. And this is divided by, so this is negative 1.9 times 10 power 10 joules. Rockets of the satellite are fired for a short time. The satellite's orbit is now closer to the surface of the planet. The orbit is closer to the surface of the planet. Note that we have already seen that v squared is equal to v was the square root of gm over r, so v squared is inversely proportional to the radius of orbit. State and explain the change, if any, in the kinetic energy of the satellite. Remember, kinetic energy is a half mv squared. It is closer, it means this has reduced. If this has reduced, it means this has increased. And if this has increased, it means kinetic energy has increased. So we are saying v squared is inversely proportional to r. Since r is smaller, since r is now small, the speed is now greater. The speed is greater, so the kinetic energy is going to be greater. State three features of the orbit of a geostationary satellite. One, it is just above the equator. Two, it has a period of 24 hours. 3, it orbits west to east. So it is just above the equator, has the same period as the rotation of the Earth, orbits in the same direction as the direction of spinning of the Earth. Okay. 2-point masses are separated by a distance x in a vacuum. State the expression for the force F between the two masses, capital M and small m. State the name of any other symbol used. So the force F is equal to capital G, capital M, small m over x squared, where G is the universal gravitational constant. V is the universal gravitational constant. Next, a small sphere S is attached to one end of a rod as shown in the figure below. So we can see a sphere is attached to one end. Okay. The rod hangs from a vertical thread as we have seen and is horizontal. The distance from the center of the sphere S to the thread is 8 centimeters. So this distance is 8. A larger sphere L is placed near to sphere S as shown. There is a force of attraction between spheres S and L, causing sphere S to move through distance 1.2 millimeters. Okay, the line joining the centers of S and L is normal to the field. So the line is normal to the rod. So this line here, the line joining the centers is perpendicular. I want it here. This is 90 degrees. So it means the weight of this would be downwards, or the force between the two spheres could be attractive towards each other. So that the angle theta through which the rod rotates is given by that. So notice that they have said causing sphere S to move through a distance of 1.2 millimeters. So it moves through a small distance. So it means the angle theta is approximately equal to the arc length S over the distance or the radius r, the distance through which the rod moves through. That means theta is going to be equal to 1.2 times 10 power negative 2 divided by r. Of course, I've used small angles. For small angles, if theta is very small, then the arc length over the radius is equal to theta. So this is over 8.0 times 10 power negative 2. By the way, this is negative 3. Pressing the calculator, so this is giving me 1.5 times 10 power negative 2 radians. Because this is radians, for small angles, theta is equal to the arc length over the radius. Then the rotation of the rod causes the rod to twist. The torque T in Newton meters required to twist the thread through an angle beta in radians is given by that. That is the expression for the torque. Calculate the torque in a thread where L is positioned as shown in the figure 1.2. If L is positioned as shown in the figure 1.2, this is what we have. Beta will be equal to theta. So beta is the same as theta in that position. So beta is going to be equal to the same as theta. But they have told us to calculate the torque. So this means T. In that position, beta is equal to theta. If L is positioned the way it is, beta is equal to theta. So the torque is going to be 9.3 times 10 power negative 10 times theta, which is 1.5 times 10 power negative 2. Answer. This is 1.4 times 10 power negative 11 Newton meters. Then The distance between the centers of spheres S and L is 6 centimeters. You have seen that in the diagram. The mass of spheres S is 7.5 grams and the mass of sphere L is 1.3 kilograms. By equating the torque in B to the moment about the thread produced by gravitational attraction between the spheres, calculate the value of the gravitational constant. So coming back here, the gravitational attraction is acting perpendicular. So its perpendicular distance is going to be this one here. Its perpendicular distance is going to be that one, which is still 8 times 10 power 8 centimeters. So the moment caused by the gravitational force will be this force times its perpendicular distance above this point. And we are going to equate it to the torque. And remember, gravitational force F is equal to capital G, capital M, small m over r squared. So one of this can be capital M, this will be small m over the distance between them, which will be r squared. So we are now back here. By equating the torque, which torque is 1.4 times 10 power negative 11, to the moment about the thread produced by the gravitational force, which will be the gravitational force times the perpendicular distance, which is 8 times 10 power negative 2, which is the same as, remember, the force is going to be capital G, capital M, small m over r squared. They said they want us to find the value of the gravitational constant, capital G. So we are going to simply say that 1.4 times 10 power negative 11 is equal to F. I'm putting F for this. So that will be G times capital M, let it be 1.3 times small m, let it be 7.5 times 10 power negative 3. Then divide by the square of the separation, which is 6.0 times 10 power negative 2, but it is squared. And this is times this distance, because it is moment is force times perpendicular distance. 8.0 times 10 power negative 2. Make G the subject. I don't always want to do that. I just want to press my calculator, but capital G is going to be equal to 1.4 times 10 power negative 11, 6.0 times 10 power negative 2, but it is squared, 1.3, 7.5 times 10 power negative 3, 8.0 times 10 power negative 2. I press my calculator. So I'm finding G as 6.4 times 10 power negative 11. 6.4 times 10 power negative 11. Okay. Suggest why the total force between the spheres may not be equal to the force calculated using Newton's law of gravitation. Remember, Newton's law is only applicable to point masses where their separation is far, far greater than the size of n of them. Their separation is far, far greater than the diameter of n of them. But we say the separation was 6 centimeters from the centers. It was 6 centimeters, and one mass was 1.3 kilograms, the other one was 7.5. So it means these two cannot really be considered to be point masses. So somebody would simply say the law only applies to point masses. but the spheres are not point masses. The law only applies to point masses, but the spheres are not point masses. That's one way of thinking about it. By the way, the spheres may also be charged. That means the electrostatic force between the spheres may affect. So spheres may be charged, so maybe there may be electrostatic force between the spheres. The spheres may be charged. So the force is not only due to their masses if they are charged. Okay. Also, you could also think about the spheres and may not be uniform. Therefore, because Newton's law only applies on uniform spheres, the spheres may not be uniform. This is another way of stating this. The spheres may not be uniform. The law only applies on uniform spheres. Or you could look at them as the masses are not isolated. You can say the masses are not isolated. If they're not isolated, it means they are very close to each other. So one experiences um, one can experience a force to another. This is also possible if there are how do I write electrostatic? Electrostatic. Alternatively, you can also say the radii of the spheres are not small compared with their separation. That means the same. When I say the law only applies to point masses and spheres are not point masses, I can also say the radii of spheres are not small compared with separation. Okay. By the way, there could also be a force between between L and the rod because the rod also has a mass. Let me even change the color. There could be a force between L, that is the sphere L, and the rod. There is a force between L and the rod that affects the results. That also makes the value we have obtained not, or the force between the spheres may not be equal to the one calculated using Newton's law because there could be a force between L, that is the sphere above, and the rod itself. Okay, let's continue as we wind up. 2-point masses are isolated in space and are separated by distance x. State an expression relating F and the two masses m and small m. State the name of any symbol used. So force is equal to capital G, that one is not given, capital M is given, small m is given, over x squared. G is the universal gravitational constant. Okay. A spacecraft is to be put into a circular orbit about a spherical planet. The planet may be considered to be isolated in space. The mass of the planet is assumed to be concentrated at the center and is that the radius of the planet is given at 3.4 times 10 power 6. The spacecraft is to orbit the planet at a height of 2.4 times 10 power 5 meters above the surface of the planet. At this altitude, there is no atmosphere. Show that the speed of the spacecraft in its orbit is that. So remember, gravitational force provides the centripetal force. So mv squared over x will be equal to capital G, capital M, small m, x squared. So small x cancels, small m cancels. V is going to be the square root of capital G, capital M over x. We substitute. V will be equal to the square root of 6.67 times 10 power negative 11, 7.5 times 10 power 23. Then x is now, it is at this height. The radius of the planet is that. So x is going to be 3.4 times 10 power 6 plus 2.4 times 10 power 5. And this gives you, I will just move one step here so that this becomes 3.64 times 10 power 6. Pressing my calculator. So this is giving me 3.7 times 10 power 3 meters per second as V. So one possible path of the spacecraft as it approaches the planet is shown in the figure. Okay. So here it is at a distance of that from the center, and here is at that distance. The spacecraft enters the orbit at a point A, enters the orbit at point A with a speed of 3.7 times 10 power 3. At B, it is at a distance of that. This distance from the center of the planet, the spacecraft has a speed of that. So here it has this speed. The mass of the spacecraft is 650. For the spacecraft moving from point B to A, show that the change in gravitational potential energy is given by this value here. So first of all, we know that potential energy is equal to negative capital G, capital M, small m over distance. So if you want, you can first of all find the potential energy at B, potential energy at A, then subtract. I think let me do that. To this time, let me do that. So potential energy at A is going to be negative 6.67 times 10 power negative 11. The mass of the planet was 7.5 times 10 power 23. The mass of the spacecraft is 650 divided by the distance, which is 3.64 times 10 power 6. Answer negative 8.93 times 10 power 9 joules. Get the potential energy at B. So this is negative 6.67 times 10 power negative 11 times 7.5 times 10 power 23 times 650 divided by, at B it is 5.64 0.00 times 10 power 7. I just change this from my calculator. So this is negative 6.50 times 10 power 8 joules times 10 power 8 joules. So the change in potential energy, I'll get this. I'll get this minus that. So that is potential at B minus energy at A, which is negative 6.50 times 10 power 8 minus negative 8.93 times 10 power 9. So this is giving me 8.28 times 10 power 9, which is the change in potential energy is approximately 8.3 times 10 power 9 joules. Okay, by considering changes in gravitational potential energy, and in kinetic energy of the spacecraft, determine whether the total energy of the spacecraft increases or decreases in moving from point B to point A. Of course, potential energy decreases. We are moving from infinity or from a further distance closer to the planet. It means the potential energy decreases. But of course, when potential energy decreases, um, and by considering changes in gravitational potential energy and in kinetic energy of the spacecraft, determine whether the total energy of the spacecraft increases or decreases in moving from point B to point A. So at point B, it had this speed. At point B, the spacecraft has speed of 4.1 times 10 power, but at point A it has this speed, so kinetic energy has decreased. So kinetic energy decreases because the speed has decreased. Kinetic energy decreases. In bracket, you have seen that the speed decreased. We started with 4.1, we are now with 3.7. Speed decreases from 4.1 times 10 power 3 meters per second to 3.7 times 10 power 3 meters per second. So kinetic energy decreases. Potential energy also decreases. So the potential energy has automatically decreased because we are moving from a higher potential to a lower potential. So potential energy decreases. So the total energy automatically decreases. If kinetic and potential have both decreased, then total energy has decreased. State Newton's law of gravitation, force between two point masses. I think this could be the last time we are stating this law. The force between 2-point masses is directly Now some people will be referring to the force between 2-point mass, yet it is mass is singular. So the force between 2-point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation, to the square of their separation. Let me just say their separation. And inversely proportional to the square of their separation. At this point, you cannot fail to state Newton's law of gravitation. A distant star is orbited by several planets. Each planet has a circular orbit with a different radius. Each planet orbits at a constant speed. Explain whether the planets are in equilibrium. A distant star is orbited by several planets. Each planet has a circular orbit with a different radius. Explain each planet orbits at a constant speed. Now, when people see constant speed, they will immediately think it is in equilibrium. Yet there are orbits involved here. Equilibrium is only when we are dealing with a straight line. If the speed is constant in a straight line, we have equilibrium. So one is even though the speed is constant, the velocity changes since direction of motion changes. So the velocity changes since direction of motion changes. And if the velocity changes, there is an acceleration. And if there is an acceleration, there is a resultant force. Thus, they are not in equilibrium. So because they are moving in orbits, it means even though the speed is constant, the velocity is not constant, the velocity changes since the direction of motion changes. And if the direction of motion changes, there is an acceleration. So there is a resultant force if there is an acceleration. So we say it's not in equilibrium. Okay. The radius of the orbit of a planet is r and the period is t. Data for some of the planets is given. Planet C, planet E, planet G. They have given you the radii here. The periods have been given. The relationship between r and t is given by the expression r cubed is equal to kt squared. Show that the constant k is given by that expression there. So we know that the gravitational force provides the centripetal force. Gravitational force provides centripetal force. So capital G, capital M, small m over r squared will be equal to small m v squared over r. Do not forget v is equal to omega times r. Omega is 2 pi over t, so this will be times r. Small m has cancelled, r reduces with the square, so we remain with capital G, capital M over r is equal to, we substitute for v, 4 pi squared r squared over t squared. So when I make show that the constant k is given by that. So rearranging this, I have that G times M times t squared is equal to 4 pi squared r cubed. So it means r cubed is going to be equal to G m over 4 pi squared times t squared, and G m over 4 pi squared is equal to k, which is a constant. So gravitational force provides the centripetal force. Then we do the simple algebra as usual. Use data in the figure for the 3 planets and expression for k to calculate the mass. Use data for the 3 planets and expression for k to calculate the mass. So for the 3 planets, remember, we can verify the k. So let's say for C, let's see what k is. We have that r cubed over t squared is going to be equal to 9.6 times 10 power 10 from the table, that is r. Then t is given as 2.5 times 10 power 11. And this is, okay, this is given as t squared, so I don't need to square it. But this one is given as just r, so this will be r cubed. Answer. I'll have these to 3 significant figures and I see what happens. So to 3 significant figures, I'm finding 3.54 times 10 power negative 21. That's the first constant. Then if I consider planet E, again r cubed over t squared, I have 4.0 times 10 power 11 for E, divided by 1.8 times 10 power 13. By the way, this is cubed. So I'm getting 3.56 times 10 power 21. I can still check for planet G, where r is 2.1 times 10 power 12, but this should be raised power 3, divided by 2.6 times 10 power 15. So this is 3.56 times 10 power 21. So on average, I can use k as approximately 3 point. I can get the average of those values as my value of k. So I'll use k is going to be the average. Let me say 3.54 plus 3.56 plus 3.56 divided by 3. So k is going to be 3.55 as the average times 10 power 21. That is the k. But remember, k is equal to capital G, capital M over 4 pi squared. So m is going to be 3.55 times 10 power 21 times 4 pi squared divided by G, which is 6.67 times 10 power negative 11. So this is giving me 2.1 times 10 power 33 kilograms. You can verify. So I couldn't use one value of k because the most appropriate value of k would be the average. That's why I did for all these 3, or at least you could do for 2 of the planets. Okay, next. A gravitational field may be represented by lines of gravitational force. State what is meant by a line of gravitational force. A line of gravitational force, or the gravitational field line. Sometimes it is like that. So the line shows the path in which a small test mass will move. It shows the direction of the path in which a small test mass would move. That is the field line. So it is the direction of the force on a small test mass. The direction of the force on a small test mass. So that's what we call the gravitational field line, the direction of the force on a small test mass. Or it is the direction of the path. The direction or the path, let me just say direction or the path in which a small test mass will move. The direction in which a small test mass will move is what we call the direction of the gravitation of the line of gravitational force. Because the small test mass moves in the direction of the gravitational field, so it moves in the line of the gravitational force. By reference to lines of gravitational force near to the surface of the Earth, explain why the gravitational field strength close to the Earth's surface is approximately constant. Why G close to the Earth's surface is approximately constant? One, the lines of force are actually radial. The field lines or the lines of force are radial, but the height above the surface is always much smaller compared to the radius of the Earth. So the radial field lines will be approximately parallel again, and the parallel lines imply constant field strength. So we know that the lines of force are supposed to be radial. Because there are many marks, I will say the lines of force or the field lines are radial. The field lines are radial. They are supposed to be radial. Because for the Earth, the field lines are actually radial. But at a height close to the surface, but at a height, close to the Earth, at a height close to the Earth, the height is much smaller. Is much smaller compared to the large radius of the Earth. To the large radius of the Earth is much smaller compared to the large radius of the Earth. So the field lines are approximately parallel. The field lines are approximately parallel, and we know parallel field lines, parallel lines imply constant field strength. Alternatively, they said by reference to the lines of gravitational force near to the surface of the Earth. at height above the Earth's surface, that height is always much smaller compared to the large radius of the Earth. So when you come close to the Earth's surface, the field lines, which are actually radial, but close to the Earth's surface, they are approximately parallel, and the parallel lines imply constant field strength. That is the explanation to that. The Moon may be considered to be a uniform sphere of diameter that, and the mass is 7.4 times 10 power 22 kilograms. The Moon has no atmosphere. During a collision of the Moon with a meteorite, a rock is thrown vertically up from the surface of the Moon with a speed. So the rock is thrown with that speed. During a collision, the rock is thrown with that speed. Assume that the Moon is isolated in space. That means the law of gravitation can apply. Determine whether the rock will travel out into distant space or return to the Moon's surface. If the minimum speed required is actually less than this, it means it will go out, because this is the one with which it is thrown. But we can find a minimum speed for the rock to escape. If the minimum speed is greater than this, then it will just return, because this is what is thrown with, but there is a minimum. So we can find a minimum. Determine whether the rock will travel out into distant space or return to the Moon's surface. So during collision, first of all, before we look at this speed, what is the minimum speed required? So the change in kinetic energy of the rock should be equal to the change in the potential energy. So the change in kinetic energy is going to be a half mv squared, and the change in potential energy is capital G, capital M, small m over r. So this is going to be a small m has cancelled. So v squared, or v is going to be the square root of 2 times capital G times m over r. So when I substitute, this is going to be 2 times 6.67 times 10 power negative 11 times m, that is 7.4 times 10 power 22, divided by the way, if it is a free, then at infinity potential energy is 0, then from the surface it is this. That's why I've just considered this. Otherwise I would just say 0 minus negative of that, which would give me this value here. So this is divided by r, which r is the diameter is this, so the radius distance from the center is 1.7 times 10 power 6 in meters. So this is 1.7 times 10 power 6 in meters. I'm finding the answer here, pressing the answer. So this is giving me 2.4 times 10 power 3 meters per second, which is 2.4 kilometers per second. Of course, this value here, this is the minimum speed required to escape, but it is thrown with this speed, so it means it will escape. It will escape. Alternatively, you could find the mass which corresponds to this. The mass which corresponds to this value of speed. If the mass which corresponds to this value of speed is less than the mass of the Moon, it still implies the same. But the easiest one to look at is the speed. If this is speed 2.8 kilometers per second, the speed with which it is thrown is greater than the minimum speed required for it to escape. Is greater, the speed 2.8 kilometers per second is greater than the minimum speed. The minimum speed required. the minimum speed required to escape. So the rock will travel out. So the rock will travel out into distant space. So this conclusion gives you the fourth mark. Of course, this one has given you one mark, another mark, another mark, and the fourth mark from the conclusion. I said you could also look at the masses, but you could use the same formula. Of course, instead you can use the the velocity given. This is what I'm saying. The loss in change in kinetic energy is equal to change in potential energy. So I have a half times m. Where there is speed, I put 2.8 kilometers, which is 2,800. But this is squared, which will be equal to the mass times capital G times capital M divided by R, which R is still 1.7 times 10 power 6. So small m cancels, and still I am trying to find capital M. When I find capital M will be equal to 2,800 squared times 1.7 times 10 power 6 divided by 2 times 6.67 times 10 power negative 11. I get my answer here. So the answer here is 1.0 times 10 power 23 kilograms. So the mass here is actually greater than the mass of the moon. The mass which corresponds to this speed, the mass which needs or which causes this speed here is greater than the mass of the moon. That means the speed which we have given is greater than the minimum speed. Therefore, still, so I'll say 1 point, is it 22, 23? I hope I calculated correctly. I'm very tired. That is it. So I have 2,800 squared times 1.7 exponent 6 divided by 2, 6.67 exponent negative 11. Yeah, it is power 22. So the mass m is less than the mass of the moon. In other words, the mass corresponding to this speed is less than the mass of the moon. That means the reverse is true, the minimum, because remember V is equal to the square root of Gm over R. So it means the speed, this mass is less than the mass of the what? The mass of the this mass is less than the mass of the moon. So it means the speed with which this speed here is actually greater than the minimum speed. If this mass is less than the mass of the moon. So we are saying 1.0 times 10 power 22 is less than 7.4 times 10 power 22 kilograms. So it will travel out. If this mass was greater than the one of the moon, then the reverse would be true. It means the speed which you have been given would be less than the minimum speed required. Okay, I think we are off to the last or second last question. Gravitational potential. The work done in moving a unit test mass from infinity to a point or to the point. Suggest why for small changes in height near the Earth's surface, gravitational potential is approximately constant. Gravitational potential. Gravitational potential is negative G capital M over R. Close to the Earth's surface, the height is much less than the radius. So close to the Earth's surface, the height is much less. This is very important. Is much less than the radius of the Earth. In other words, the radius, if I get the radius plus the height is approximately the same as the radius. And we know that potential is inversely proportional to radius. Potential is inversely proportional to the radius, and the radius is approximately constant because for smaller height, height is much less than the radius, so the radius of orbit is approximately constant. The potential is inversely proportional to the radius, and the radius is approximately constant. So potential is approximately constant. By the way, you can do this mathematically, and you say potential is equal to negative Gm over R. Potential at a height h is going to be negative Gm over R plus h. But for h far, far less than R, R plus h is approximately R, which means that potential at height h is approximately the same as the potential just on the surface. For h far, far less than R, R plus h is approximately the same as R. So potential at h is approximately the same as potential on the surface. Okay? The moon may be considered to be a uniform sphere with a diameter of that. And this mass is that a meteorite strikes the moon, and during the collision, a rock is sent off from the surface of the moon with an initial speed. It's almost a repetition, I think, with an initial speed of v. Assume that the moon is isolated in space. Determine the minimum speed of the rock such that it does not return. So if it is isolated in speed, so the change in kinetic energy, assuming it starts from 0, so we can say initial kinetic energy should be equal to the potential energy at the surface. I'll just put here negative to cancel the negative of potential energy at the surface. The initial kinetic energy will be equal to the potential energy at the surface, because if at infinity, total energy is 0. That means the initial kinetic energy should be equal to the potential energy at the surface. So I have mv squared is going to be equal to g m over r. This cancels. So v is going to be equal to the square root of 2 times 6.67 times 10 power negative 11, 7.4 times 10 power 22 divide by 0.5 times 3.5 times 10 power 6. Because they gave me diameter of 3.5. I'm trying to change it to radius. That's why you see 0.5 here. It is a half of diameter. When I press the calculator here, so in two significant figures, you have 2.4 times 10 power 3 meters per second. Last but not least, state what is meant by gravitational field strength. We have already said this is the force per unit mass. Force per unit mass. The force acting on a unit test mass placed in the region of the gravitational field. Explain why at the surface of a planet, gravitational field strength is numerically equal to the acceleration of free fall at the surface of a planet. First of all, acceleration is equal to the force per unit mass. And also the field strength. This one is from Newton's second law. And also the field strength is equal to the force acting on a unit mass. So they are equal. The acceleration is force per unit mass. The field strength is force per unit mass. So they are equal. The acceleration is force over mass. The field strength is the force acting on a unit mass. So the two are equal. And part B, an isolated uniform spherical planet has radius r. The acceleration of free fall at the surface is g. So r should be at g 1.00 g. So that is the surface. G is acceleration due to gravity is g on the surface, where the surface is after a distance r from the center. Sketch a graph to show the variation of the acceleration of free fall with the distance x from the center of the planet for values of x ranging from x is equal to r to x equals to 4. So we shall not mind about what is happening inside the planet. We shall start from the surface. So note that g is equal to capital Gm over x squared. So for g at a distance r, this is capital Gm over r squared, which is just g. For g at a distance to r, this is going to be capital Gm. Where there is x, I put there 2r, but it is squared, which becomes a quarter of Gm over r squared, which is a quarter of g, or 0.25 g. Then you can also check g at 3r. So it's just put here 3r, it becomes 1 over 9 of g. 1 over 9 of g is 0.11, I think, of g. 1 divided by 9. Then we get g at 4r, which will be, when I put 4r, it becomes 1 over 16g. 1 divided by 16 is 0.0625. Okay, now you have the scale. One small square is 0.025. You divide this by 10. So one small square represents 0.025. So the first one, this is easy. It starts from there. At 2r, it is 0.25. So at 2r, you put there your ruler. I think it is this point here. At 2r, that is the point. Then at 3r, 0.11 g. So I divide 0.11 divide by the scale 0.025. So I'll count 4 small squares, almost 5. 1, 2, 3, 4. Somewhere here. That's where I will have 0.11 g. Then at 4r is 0.0625 times g. So I get 0.0625 divided by the scale 0.025. Those are 2.5 small squares. So I have 1, 2.5. This one is very important. They will mark exactly half. Okay, so I have those points. I just sketch a graph through them. It's not very easy using a computer to sketch, but I'm going to try. So my graph will go like that. For you can sketch a better one because you have the document in hard copy. So precisely that is, I don't want to repeat through it, but precisely this is how the graph would look like. You can draw a better one. You can draw a better one using in your book or on your document, on your paper. So the purpose is not to cram the shape of the graph. What is important is to arrive at to understand how they come up with the graph, and that is all. Lastly, the planet in B has a radius r, which is equal to 3.4 times 10 power 3 kilometers, and density 4.0 times 10 power 3 kilograms per meters cubed. Calculate the acceleration of free fall at a height r above its surface. Calculate the acceleration of free fall at a height r above its surface. Acceleration of free fall, that is g. So g is equal to capital G, capital M over r squared. And they have given us density, so we know that mass is equal to density times volume, which will be density if we assume it is spherical, so that will be volume of a sphere 4 over 3 pi r cubed. So I'm now substituting. So G is going to be equal to capital G times 4 pi r cubed, of course, times the density, divided by 3 times, now this distance here, they said the planet has a radius r. Calculate the acceleration of free fall at a height r again above its surface. So let me change this to radius first. Distance from the center to the required point. And this one is also distance from okay, that one is fine. So this is going to be 3 into, because this is at a height r, so this would be r plus r squared, which becomes twice r. When you square it, it becomes 4. So it becomes 12r. So this is g times 4 pi r cubed times density divided by, this is 2r. It becomes 4r squared, which becomes 12r squared. So this one reduces the power of that. I'm now substituting 6.67 times 10 power negative 11 times 4 pi times 3.4 times 10 power 6 times the density 4.0 times 10 power 3 divide by 12. Oh, 6.67, 4 pi, 3.4 exponent 6, 4.0 exponent 3, divided by 12. So this is 0.95 meters per second squared. So that is the end of gravitation. If you have followed through all these equations, you must have gained confidence in gravitation. If you haven't gained confidence in gravitation, then there is no any other better way I can help you. I beg to hang up here. When we join school, when school starts, we shall be looking at electric fields. For now, I wish you a nice holiday. Bye bye.